Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us out into the vastness of the glittering world of deep space. All that we see above us, the dark velvet canvas pricked with tiny points of light, is just the shore of a cosmic ocean. Beyond our small, quiet world, the universe breathes in slow, ancient rhythms. Galaxies spin in silent, majestic spirals. Vast clouds of dust and gas patiently wait to be born into new stars. And old light, having traveled for millions of years, finally arrives to paint a picture of the distant past for us to see. This immensity is not cold or empty. It is full of patient, quiet processes, a grand, slow dance of gravity and light that has continued for an eternity. When you look up into that darkness, it is easy to feel small, but you are also looking at the very substance from which you came. Every element in your body was forged in the heart of a star that lived and transformed long ago. You're a piece of this cosmos, looking back at its own home. Tonight, we will not be overwhelmed by the scale, but instead, we will be cradled by it. We will let the silence of the void become a peaceful quiet, and the endless expanse a soft blanket of wonder, allowing your mind to drift peacefully among the stars. If you enjoy these quiet explorations, consider subscribing so you can easily return here whenever you need to rest. For now, get comfortable. Let your eyes grow heavy. Let's begin. The light from our sun that warms your face has actually been traveling for over 8 minutes to reach you. When we look at the sun, we are never seeing it as it is in this exact instant, but rather as it was in the recent past. The universe is so vast that even light, the fastest thing we know, requires time to cross the massive distances between celestial bodies. The sun rests at the heart of our solar system, an immense sphere of glowing plasma about 93 million miles, or 150 million kilometers away, holding us in its gentle gravitational embrace. Light travels at an incredible speed of 186,282 miles per second, or about 300,000 kilometers per second, in the vacuum of space. Yet even at this blistering pace, the journey from the sun's fiery surface to the surface of our planet is not instantaneous. It requires approximately 8 minutes and 20 seconds for a single photon of light to complete that journey. This means that if the sun were to suddenly and magically vanish, we would continue to see it shining, continue to feel its warmth for more than 8 full minutes before the darkness and the cold would suddenly arrive. This quiet, built-in delay is a constant reminder of the immense scale of our own solar neighborhood, a cosmic echo built into every sunrise. Every ray of light is a tiny time capsule, a gift from the recent past, connecting us directly to the heart of our star. The largest known volcano in our entire solar system is found not on Earth, but on the quiet, red surface of Mars. We think of our own world as a place of dramatic geology, with towering mountains and explosive volcanoes, but our solar system is filled with wonders that dwarf our own. And on the rusty, dusty plains of Mars, a planet with a much thinner atmosphere and a colder heart, lies a geological feature of truly staggering proportions. This colossal mountain is named Olympus Mons, and it stands nearly 14 miles high, or about 22 kilometers, making it almost 3 times the height of Mount Everest. Its base is so enormous that it would cover an area roughly the size of the state of Arizona, or the entire nation of France. If you were to stand at its edge, the slope would be so gentle and gradual that you wouldn't even be able to see the summit. The peak would be hidden far beyond the curve of the planet itself. Scientists believe it grew so large because Mars has lower surface gravity, and unlike Earth, its tectonic plates are not thought to be active, allowing the volcano to stay over a single, stationary hotspot for billions of years, patiently building itself layer by layer with slow flows of lava. Olympus Mons is now a sleeping giant, a silent monument to the fiery, active past of a world that has since grown quiet, resting as a testament to the power of time and the dramatic forces that shape worlds. On the planet Venus, a single day lasts longer than an entire year. We are accustomed to the familiar rhythm of Earth, where our day is a brief 24-hour spin and our year is a leisurely 365-day journey around the Sun. This cycle of day and night, of seasons, defines our very perception of time. But when we look to our celestial neighbors, we find that time itself behaves in strange and wonderful ways. Venus, our sister planet, is shrouded in thick, toxic clouds, a world of intense heat and crushing pressure. This planet has a remarkably slow and lazy rotation, taking about 243 days on Earth to spin just once on its axis, which constitutes one Venusian day. However, its orbit around the Sun, its year, is much faster, taking only about 225 Earth days to complete. This creates a bizarre reality, where the planet completes its annual journey around the Sun before it has even finished a single day's rotation. Furthermore, Venus spins backwards, or in retrograde, compared to most other planets, meaning the Sun, if you could see it through the thick clouds, would appear to rise in the west and set in the east. This strange, languid dance of Venus is a beautiful reminder that our own experience of time is just one local variation, and that the universe does not share our clocks, as each world spins to its own ancient, unique, and unhurried rhythm. The magnificent, iconic rings of Saturn are not solid structures, but are instead composed almost entirely of countless particles of water ice. From Earth, Saturn is a jewel in the night sky, its rings appearing as a solid, graceful halo. They seem serene, perfect, and unchanging, a symbol of cosmic elegance. For centuries, astronomers wondered about their true nature, imagining them as solid disks, or perhaps clouds of dust. It is only as we have drawn closer, through the lenses of powerful telescopes and the eyes of robotic probes, that the rings have revealed their true, shimmering secret. These rings are not solid at all, but rather an immense, flattened swarm of individual pieces of ice, all orbiting Saturn together like a vast, glittering river. These particles range in size from tiny, dust-like specks to chunks as large as a house or even a small mountain. The entire system of rings is incredibly thin, in most places only about 30 feet thick, or around 10 meters, even though they stretch out for over 175,000 miles, or 282,000 kilometers. Scientists believe these ice pieces are the shattered remnants of comets, asteroids, or perhaps a moon that was torn apart by Saturn's immense gravity long ago. The rings are not a permanent feature. They are in a slow, patient process of disappearing, with ice raining down onto the planet's atmosphere. We are merely lucky to exist in an age where we can witness this ethereal, icy crown in all its majestic temporary glory. Jupiter's famous Great Red Spot is actually a gigantic swirling storm that has been raging for centuries. The planet Jupiter is the king of our solar system, a colossal gas giant of swirling clouds, bands of color, and turbulent weather. It has no solid surface to stand on, only an atmosphere that grows denser and denser, transitioning into a strange, metallic ocean of liquid hydrogen far below. Within this chaotic and beautiful atmosphere, One feature has captivated human observers for hundreds of years. This feature, the Great Red Spot, is an anticyclonic storm, a high-pressure system so vast that it is wider than the entire planet Earth. At its largest observed size, it was wide enough to fit 3 Earths side by side, with winds at its periphery howling at speeds of over 270 miles per hour, or 430 kilometers per hour. We know it has been churning for at least 190 years since it was first clearly identified, and it may well be the same storm noted by astronomers as early as the 1600s. Unlike hurricanes on Earth, which form over warm oceans and weaken over land, this storm is powered by Jupiter's internal heat and has no land to stop it, allowing it to persist for an immense, unknown period of time. In recent decades, we have watched this ancient storm slowly shrinking, a sign that even the most enduring features of the solar system are in a state of gentle transformation, a magnificent swirling eye, a testament to the enduring and awesome power of nature on a scale we can barely comprehend. It is impossible to stand on the surface of a gas giant like Jupiter or Saturn, because they do not have a solid surface at all. When we imagine other worlds, our minds naturally picture landscapes, plains of rock or ice upon which we could one day walk. We see Mars and our moon, and we imagine footprints. But the largest planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, defy this intuition. They are majestic, colorful orbs, but they are worlds of atmosphere, not of ground. If you were to descend into Jupiter's atmosphere, you would simply fall through endless layers of clouds, composed of ammonia, hydrogen sulfide, and water. As you went deeper, the atmospheric pressure would increase relentlessly, becoming thousands of times greater than on Earth, and the temperatures would soar. The gas, primarily hydrogen and helium, would become so compressed that it would transition into a supercritical fluid, a strange state of matter that is neither truly gas nor liquid. Deeper still, tens of thousands of miles down, the pressure becomes so immense that the hydrogen itself is crushed into a metallic state, a sea of liquid metal that conducts electricity and generates Jupiter's powerful magnetic field. At the very center, there may be a small rocky core, but it is forever buried beneath an ocean of exotic, crushed elements. These planets are not places to visit, but rather places to observe in awe. Great, swirling oceans of gas that challenge our very definition of a world. Our own Milky Way galaxy is on a collision course with its nearest large neighbor, the Andromeda Galaxy. We look out from our small planet and see our galaxy, the Milky Way, as a vast, stable river of stars across the night sky, feeling like it is our permanent, unchanging home in the cosmos. We are one of perhaps hundreds of billions of galaxies, each a separate island universe. But these islands are not static. They are all moving, pulled by the invisible, patient hands of gravity. The Andromeda Galaxy, a beautiful spiral similar to our own, and visible as a faint, fuzzy patch of light to the naked eye, is currently about 2.5 million light-years away. However, it is hurtling toward us at a staggering speed of about 250,000 miles per hour, or 400,000 kilometers per hour. This grand cosmic dance will result in a majestic merger, though it is not an event we need to worry about, as this transformation is scheduled to begin in about 4 to 5 billion years. When it happens, it will not be a violent crash of stars. The space between stars is so vast that individual stars will almost certainly not collide. Instead, the two galaxies will pass through each other, their gravitational fields tangling, distorting their elegant spiral arms and pulling them into vast, streaming tails. Over millions of years, the two will settle together, their stars mingling to form a single, new, giant elliptical galaxy, a slow, majestic, and creative transformation, reminding us that the universe is a dynamic and ever-evolving work of art. There are more stars in the observable universe than there are grains of sand on all the beaches and in all the deserts on Earth. We often try to grasp the scale of the cosmos with comparisons, but the numbers involved quickly overwhelm our imagination. We can try to picture the sand on a single beach, then all the beaches in the world, and then all the deserts, a number so vast it feels infinite. And yet, this is the measure we must use when we look up at the night sky and contemplate the true number of suns. Scientists have estimated that our own Milky Way galaxy contains at least 100 billion stars, and this is just one modest galaxy. By observing the deepest parts of space, we have learned that there are at least 2 trillion galaxies in the observable universe, each one a massive collection of stars, gas, and dust. When you multiply these numbers, the total count of stars becomes almost meaningless, a number with 22 to 24 zeros after it. In contrast, the estimated number of sand grains on Earth, a calculation based on the average size of a grain and the total volume of sand on the planet, is a mere 7.5 quintillion, a number with only 18 zeros for every single grain of sand you could ever hold. The universe has prepared at least 10,000 stars, and perhaps many more. This simple, profound fact doesn't make us small. It makes the universe unimaginably rich, a place of infinite possibility and endless light. The famous pillars of creation are actually colossal, towering columns of interstellar gas and dust, where new stars are being born. In 1995, the Hubble Space Telescope returned an image that became an icon of modern astronomy, showing 3 immense, ghostly towers standing against a backdrop of stars. They looked like mystical structures, vast monuments sculpted by a cosmic hand, but these pillars are not solid, nor are they silent. They are a dynamic, turbulent, and creative place. Located about 7,000 light-years away in the Eagle Nebula, these pillars are vast clouds of cool molecular hydrogen. The tallest of them is estimated to be about 4 light-years high, a distance so great that light itself takes 4 years to travel from its base to its tip. Within these dense, dark clouds, gravity is patiently at work, as small, dense knots of gas and dust are collapsing under their own weight. They grow hotter and denser until they ignite with nuclear fusion, becoming brand new stars. These newborn stars, however, are also agents of destruction for the pillars themselves. The intense ultraviolet radiation from nearby hot, young stars is eroding the pillars, sculpting them and causing the gas to evaporate, a process called photoevaporation. We are seeing these pillars in a fleeting, dramatic moment of their existence, stellar nurseries and cosmic cradles, and in their beautiful, slow-motion destruction, they are simultaneously giving birth to new suns and being swept away by the very light they have helped create. The footprints left behind by the Apollo astronauts on the Moon will remain perfectly preserved for millions of years. On Earth, nothing is permanent. The wind blows, the rain falls, and the relentless march of erosion, life, and decay smooths all surfaces. A footprint in the sand is gone in moments. A footprint in the mud is gone in days. But our Moon is a different kind of world. It is a place of profound stillness, an almost perfect vacuum. The Moon has no atmosphere to speak of, which means it has no wind to scatter dust and no rain to wash surfaces clean, It has no liquid water to erode rock and no biological life to disturb the soil. The lunar surface is covered in a fine powdery dust called regolith, the result of billions of years of meteorite impacts. When the astronauts pressed their boots into this fine powder, they created impressions as sharp and clear as wet cement. With no natural forces to erase them, these footprints, along with the rover tracks and the discarded equipment, will remain. The only force that can wear them away is the slow, steady sandblasting of micrometeorites, tiny particles of space dust that rain down. But this process is so incredibly slow that the prints will be recognizable for perhaps 10 million years or more. Those footprints are not just a record of a visit. They are a monument to human curiosity, preserved in the stillness of another world, resting patiently in the unchanging lunar dust. A neutron star is so incredibly dense that a single sugar cube-sized amount of its material would weigh as much as all of humanity combined. When a truly massive star, much larger than our Sun, reaches the end of its life, it doesn't just fade away. It collapses in on itself in a fraction of a second before exploding in a supernova, one of the most brilliant and powerful events in the universe. What is left behind, the collapsed core of that star, is one of the most extreme objects we know of, a neutron star. This object is typically only about 12 miles, or 20 kilometers, across, roughly the size of a city. Yet, it contains the mass of 1.5 to 2 times that of our entire Sun. During the collapse, the gravitational pressure is so immense that it overcomes the forces that keep atoms separate. Electrons and protons are crushed together to form a substance made almost entirely of neutrons, packed as tightly as an atomic nucleus. This neutronium is so dense that a thimbleful would weigh over 100 million tons. These stars also spin incredibly fast, some rotating hundreds of times per second, and they possess magnetic fields trillions of times stronger than Earth's. A neutron star is a stellar remnant, a ghost of a great star, but it is also a powerhouse of physics, a tiny, massive object that pushes the very laws of matter to their absolute limit. A common misconception is that black holes suck things in like a vacuum cleaner. In reality, they are just objects with extremely powerful gravity. Black holes are perhaps the most mysterious and feared objects in the cosmos. They are points of infinite density, regions of space-time from which nothing, not even light, can escape. This has given them a reputation as cosmic monsters, roaming the universe and consuming everything in their path. But the truth of their influence is far more orderly. A black hole is simply a consequence of gravity. If you were to take our Sun and replace it with a black hole of the very same mass, Earth and the other planets would not be sucked in. They would continue to orbit perfectly, just as they do now, held by the same gravitational pull. The black hole's danger zone is only its event horizon, the boundary of no return, which for a sun-mass black hole would be incredibly small, only about 3.7 miles, or 6 kilometers across. You have to get very, very close to a black hole to be in danger. It does not have an infinite reach. Its gravity, like any other object, weakens with distance. A black hole is not a predator. It is a testament to the power of mass, a deep, quiet well in the fabric of space-time, following the same laws of gravity that hold the galaxies together and keep our feet gently on the ground. The universe itself is expanding, and every galaxy is moving further and further away from almost every other galaxy. In the early 20th century, astronomers like Edwin Hubble made a profound discovery. They observed that the light from distant galaxies was redshifted, meaning its wavelength was stretched out. This was the cosmic equivalent of a siren's sound, changing pitch as it moves away from you. This observation overturned the idea of a static, unchanging universe. The universe is not expanding into anything. Rather, the very fabric of space itself is stretching. A good analogy is to imagine a loaf of raisin bread rising in an oven. As the bread, which represents space, expands, every raisin, representing a galaxy, moves further away from every other raisin. The raisins themselves are not moving through the bread, but are being carried apart by the bread's expansion. This is why it appears that we are at the center of the expansion, as everything is moving away from us. But an observer in any other galaxy would see the exact same thing. This expansion is also accelerating, driven by a mysterious force we have named dark energy, which seems to be pushing space-time apart. This cosmic expansion gives the universe a grand, sweeping narrative, a story of a hot, dense beginning, the Big Bang, and a long, slow, cooling journey toward an ever larger, ever quieter future. While space is a vacuum and cannot carry sound waves as we know them, it is not truly silent. It is filled with plasma waves that can be translated into sound. We are often told that in space, no one can hear you scream. This is true because sound, as our ears experience it, is a mechanical wave, a vibration traveling through a medium like air or water. The vast emptiness between the stars is a near-perfect vacuum, offering no medium for these vibrations to travel. However, space is not truly empty. It is filled with a thin, electrically charged gas called plasma. This plasma can carry other kinds of waves, electromagnetic waves, that vibrate at frequencies our ears cannot hear. Spacecraft like the Voyager probes, with their sensitive instruments, can detect these plasma waves. Scientists can then take the data from these waves, the frequencies and amplitudes, and transpose them into the range of human hearing. When they do this, we can listen to the chorus of Jupiter's intense magnetosphere, the eerie whistle of Earth's own radio waves, or the gentle hum of interstellar space. This music of the spheres is not sound, but a translation of the invisible electrical life of the cosmos. It is the universe humming to itself, a ghostly, beautiful chorus that reveals the hidden energies flowing through the void. Our entire solar system is thought to be encased in a vast, spherical shell of icy objects known as the Oort cloud. We are familiar with the inner solar system, the rocky planets, the asteroid belt, and the gas giants beyond Neptune. We find the Kuiper belt, home to dwarf planets like Pluto. But astronomers believe our system's true boundary lies thousands of times further out, in a realm of deep, cold darkness. The Oort cloud is a theoretical, immense cloud of icy planetesimals, the leftover building blocks of the solar system. It is not a cloud in the earthly sense, but a scattered, spherical shell of trillions of objects, extending from perhaps 2,000 to 200,000 times the distance from the Earth to the Sun. This means it could reach nearly halfway to our nearest stellar neighbor, Proxima Centauri. We have never seen an object in the Oort cloud, as they are too small, dark, and far away. We infer its existence because it is the best explanation for where long-period comets come from, comets that take thousands or even millions of years to orbit the Sun, falling in from all directions. This great icy shell is the deep reservoir of our solar system, a place of quiet, frozen remnants. It is the solar system's true, vast, and invisible border, patiently holding the ancient origins of our world's water, and, perhaps, of life itself. The Voyager 1 spacecraft launched in 1977 is the first human-made object to enter interstellar space. In the summer of 1977, humanity launched 2 probes, twin messengers, on a grand tour of the outer solar system. Together, they were designed to use a rare planetary alignment to visit Jupiter, Saturn, Uranus, and Neptune. Voyager 1 itself flew past Jupiter and Saturn, and then, using Saturn's gravity to swing northwards, continued its journey, coasting silently for decades. In 2012, it crossed a boundary called the heliopause, the point where the solar wind, the stream of particles from our Sun, gives way to the wind of interstellar space. It is now more than 15 billion miles, or 24 billion kilometers, from Earth, a distance so great that a radio signal, traveling at the speed of light, takes over 22 hours to reach it. It is adrift in the space between the stars, still sending back faint signals about the environment of the interstellar medium, powered by its slowly decaying plutonium generator. This small, old probe is our silent emissary, carrying a golden record with the sounds and images of Earth. It is a tiny bottle cast into the cosmic ocean, a testament to human curiosity that will wander the cold, quiet darkness of the Milky Way long after we are all gone. Our very nearest stellar neighbor, the star Proxima Centauri, is completely invisible to the naked eye despite its closeness. When we look up, we see bright stars like Sirius or the constellation of Orion, but these are not necessarily our closest neighbors. They are simply the brightest. The most common type of star in our galaxy is a small, dim, and cool star known as a red dwarf, and our closest neighbor happens to be one of these quiet, unassuming stars. Proxima Centauri is part of the Alpha Centauri star system, just 4.24 light-years away, while its 2 companions, Alpha Centauri A and B, are bright and sun-like. Proxima is a faint red dwarf. It has only about 12% of the Sun's mass and shines with less than 1% of the Sun's brightness. It is so dim that even from its close proximity, you cannot see it without a powerful telescope. This star is also a flare star, meaning it can suddenly and dramatically increase in brightness for short periods, unleashing powerful X-rays that would be devastating to any life on its nearby planets. This tiny, invisible neighbor is a humble reminder that the most common things in the universe are not always the most obvious. The galaxy is filled with these quiet, dim embers, patiently burning through their fuel for trillions of years, long after our own bright sun has faded. In 1977, an astronomer detected a powerful, unexplained radio signal from deep space that was so strong it was nicknamed the WOW signal. For decades, we have been listening. The search for extraterrestrial intelligence, or SETI, has involved pointing massive radio telescopes at the sky, hoping to catch a stray signal, a single hello from another civilization. For the most part, the sky has been quiet, filled only with the natural static of the cosmos. On August 15th, 1977, astronomer Jerry Ayman was using the Big Ear radio telescope at Ohio State University. He was reviewing the computer printouts of the previous night's observations when he saw a stunning anomaly. For a period of 72 seconds, the telescope had recorded a powerful, narrow-band radio signal coming from the direction of the constellation Sagittarius. The signal was at a frequency that is naturally quiet, one that scientists had long theorized would be a good channel for interstellar communication. Ayman was so astonished by the signal's strength and perfect profile that he circled it on the printout and wrote "Wow" in the margin. The signal was never detected again, despite many attempts to re-observe that patch of sky. Its origin remains a profound mystery, a single, unexplained note in the cosmic symphony, leaving us to wonder if it was a natural, undiscovered phenomenon, or the one-time whisper of something or someone else. The Goldilocks zone is the term astronomers use for the gentle, habitable region around a star where conditions are just right for liquid water to exist on a planet's surface. Life, as we know it, has one essential requirement: liquid water. It is the solvent for the chemistry of life, the medium in which biology happens. For a planet to host this precious substance, it must exist in a very special place within its solar system. It cannot be too close to its star, or the water will boil away into steam. It also cannot be too far, or the water will freeze into solid ice. This temperate orbital band is called the habitable zone, or more poetically, the Goldilocks zone. This region is not a fixed size. For a hot, bright star, the zone will be further out and wider. For a cool, dim star, like a red dwarf, the habitable zone will be much smaller, and tucked in very close to the star, our own Earth rests comfortably within our Sun's Goldilocks zone. Mars lies on its cold outer edge, while Venus is on the searing hot inner edge. The discovery of thousands of planets around other stars has become a search for these gentle oases. Finding a rocky, Earth-sized planet within its star's habitable zone is the first, hopeful step in the long, patient search for another world that, like ours, might be cradling life. Beyond the orbit of Neptune lies a vast, icy region of our solar system, called the Kuiper Belt, home to countless dwarf planets like Pluto. For a long time, Pluto was considered the lonely ninth planet at the edge of our solar system. But in the 1990s, we began to realize that Pluto was not alone. It was, in fact, just one of the largest members of an entirely new zone of the solar system, a vast, populated wilderness. This region, the Kuiper Belt, is a donut-shaped ring of icy bodies, a junkyard of material left over from the formation of the solar system. It begins at Neptune's orbit, about 30 times the Earth-Sun distance, and stretches out to about 50 times that distance. It is home to hundreds of thousands of icy objects larger than 60 miles, or 100 kilometers across, and an estimated trillion or more comets. It is here that we find Pluto, along with its brethren, other dwarf planets like Eris, Makemake, and Haumea. These are worlds large enough for their own gravity to have pulled them into a spherical shape, but not large enough to have cleared their orbital neighborhood of other debris, which is the modern definition of a planet. The Kuiper Belt is a dark, frozen frontier, a place where the building blocks of our solar system lie in a deep, cold sleep, and a beautiful, complex realm that shows us our solar system is far larger and more populated than we ever imagined. A significant portion of the universe is made of a mysterious, invisible substance known as dark matter. When we look at a galaxy, we see the bright, glittering stars, the glowing gas, and the dark lanes of dust. We can measure the mass of all this visible material, and we can observe how fast the galaxy is spinning. A profound mystery arises from this observation. The galaxies are spinning so fast that the gravity from their visible matter alone should not be enough to hold them together. They should, by all rights, fly apart, their stars scattering into the void. To solve this cosmic puzzle, astronomers have hypothesized the existence of dark matter. It is a substance that does not emit, absorb, or reflect any light, making it completely invisible to all of our telescopes. Its presence is inferred only by the gentle, persistent pull of its gravity, which acts as a cosmic glue, a vast, invisible scaffolding that holds the galaxies and indeed the entire large-scale structure of the universe. Together, scientists estimate that this invisible matter makes up about 85% of all matter in the cosmos. We are, in essence, living in a universe where the vast majority of its substance is hidden from us, a quiet, unseen presence that shapes the cosmos in the most fundamental way, its unseen hands guiding the grand, slow dance of the galaxies. The expansion of the universe is not slowing down as once thought. It is actually accelerating, driven by a mysterious force called dark energy. For most of the 20th century, astronomers debated the ultimate fate of the universe. Would gravity, the force that pulls everything together, eventually halt the cosmic expansion and cause it to collapse in a big crunch? Or would it expand forever, slowing down but never stopping? In the late 1990s, observations of distant supernovae, the brilliant explosions of dying stars, revealed a shocking truth. The expansion is not slowing down at all. It is getting faster. Some unknown influence is actively pushing space apart, overpowering gravity on the grandest scales. This mysterious pressure has been named dark energy. We do not know what it is. It may be an intrinsic property of space itself, a cost of having space, or some new exotic field. But its effects are profound. This force is estimated to make up nearly 70% of the total energy density of the universe. While dark matter works to hold galaxies together, dark energy works to push them, and the very fabric of space-time, further and further apart. It is the quiet, dominant force of the cosmos, a gentle, invisible breath that is slowly, inexorably, stretching our universe out into a vast, cold, and lonely future. Our own moon was most likely formed from the debris of a cataclysmic, planet-sized collision early in Earth's history. Our moon is a constant, familiar companion. It is so large in our sky, and its phases so regular, that it feels like an eternal part of Earth's design. Yet its origin story is one of immense ancient transformation. The leading theory, known as the giant impact hypothesis, suggests that about 4.5 billion years ago, when our Earth was still young and molten, it did not have a moon. It was struck a glancing, powerful blow by another protoplanet, an object roughly the size of Mars, which astronomers have named Theia. This was not an explosion, but a titanic merging and splashing, a cosmic event that melted both bodies and ejected a colossal amount of molten rock and vaporized material into orbit around the new, larger Earth. Over time, perhaps in just a few thousand years, gravity patiently gathered this orbiting ring of debris. The particles clumped together, coalescing into the molten sphere that would cool to become our moon. This theory elegantly explains why the moon has a chemical composition so similar to Earth's mantle, and why it has such a small iron core. Our constant, calming presence in the night sky is not a sibling or a captured visitor, but a child of the Earth, born from a majestic and formative impact, forever bound to us by the shared history of that ancient, fiery creation. Astronomers now believe that there are likely more planets in our galaxy than there are stars. For millennia, the only planets we knew were the ones in our own celestial family, the wanderers we could see from Earth. We looked up at the countless stars and wondered if any of them, too, had worlds orbiting them. In the last few decades, thanks to powerful telescopes and clever detection methods, we have graduated from wondering to knowing. We have discovered thousands of exoplanets, planets orbiting other stars. But what is truly staggering is not just the discovery of individual worlds, but the statistical implication. The data suggests that, on average, every star in the Milky Way likely hosts at least one planet. Many, like our Sun, host entire families of them. This means that when you look up at the night sky, you are not just seeing hundreds of billions of stars. You are seeing hundreds of billions of entire solar systems. There are small rocky worlds like Earth, massive gas giants like Jupiter, and strange planets in between, like hot Jupiters orbiting their star in a matter of days, or water worlds completely covered by a single global ocean. The galaxy is not a collection of lonely stars, but a vast, sprawling metropolis of worlds, a place teeming with a diversity of planets that challenges our imagination and fills the quiet darkness with almost infinite possibility. There are potentially billions of rogue planets wandering through our galaxy, untethered to any star and drifting alone in the darkness. We are accustomed to the idea of a planet as a member of a solar system, a world held in a stable, warm orbit by a parent star. But the galaxy is a dynamic and sometimes chaotic place. In the turbulent early days of solar system formation, gravitational interactions between planets can be unstable. A smaller planet can be slingshotted by its larger siblings, ejected from its home system in a powerful gravitational exchange. Other planets might form in isolation from the gravitational collapse of a small gas cloud, never having a star to call their own. These lonely worlds, known as rogue planets, sail silently through the interstellar void. They are cloaked in permanent night, their surfaces frozen solid at temperatures near absolute zero. Yet, if a large Earth-sized rogue planet has a thick hydrogen atmosphere, it could trap its own internal heat, left over from its formation, potentially allowing a vast ocean of liquid water to exist beneath a thick, icy crust. Our galaxy, therefore, may be home to a vast, unseen population of these dark, wandering worlds. They are the quiet, lost children of the cosmos, carrying the potential for hidden oceans in the cold, unending night between the stars. The speed of light in a vacuum is the absolute fastest speed at which anything in the universe can travel. In our daily lives, speed feels relative, but in the cosmos, there is a fundamental and unbreakable limit. This cosmic speed limit, the speed of light in a vacuum, is approximately 186,282 miles per second, or just under 300,000 kilometers per second. It is a speed so immense that a beam of light could circle the Earth 7.5 times in a single second. Albert Einstein's theory of relativity revealed that this is not just the speed of light, but a fundamental property of space-time itself. It is the speed of causality, the fastest that any information, any gravitational wave, or any influence can be sent from one point to another. As an object with mass approaches this speed, its own mass increases infinitely, requiring an infinite amount of energy to go any faster, which is impossible. This limit is what makes the universe so vast. It is why we cannot have an instant conversation with astronauts on Mars, and why the light from distant galaxies takes billions of years to reach us. The speed of light is the universe's ultimate law, the metronome that sets the pace for all physical interactions, ensuring that the cosmos unfolds not in an instant, but as a slow, patient, and orderly story. Our entire observable universe is believed to have burst into existence from an incredibly hot, dense state in an event known as the Big Bang. Before this moment, there was no space, no time, no matter as we know it. The concept itself is not of an explosion in space, but rather an explosion of space. The universe did not expand from a single point. into a pre-existing emptiness. Rather, the entirety of space itself began expanding, carrying energy and matter with it. In the first fractions of a second, the universe was an unimaginable inferno, 1,000,000,000,000 degrees hot, a churning quark-gluon plasma. As space expanded, it cooled, and this primordial energy began to congeal into the fundamental particles that make up our world: protons, neutrons, and electrons. It took about 380,000 years for the universe to cool enough for these particles to combine into the first atoms, primarily hydrogen and helium. At this moment, the universe, which had been an opaque, glowing fog, suddenly became transparent, allowing light to travel freely for the first time. This first light is still visible to us today. This theory is the grand, unifying story of our cosmic origins, a majestic, sweeping narrative of how an infinitely small, simple beginning could, over 13.8 billion years of slow, patient expansion and gravitational clustering, give rise to the impossibly complex and beautiful universe of stars and galaxies we see today. We can still see the very first light of the universe, a faint, ancient afterglow of the Big Bang, known as the cosmic microwave background. About 380,000 years after the Big Bang, the universe cooled to a point where atoms could form, and the cosmos, which had been a dense, hot fog, became transparent. The light that was present at that exact moment was finally set free, and it has been traveling across the expanding universe ever since. This light, which was once as hot and bright as the surface of a star, has been stretched by the expansion of space over 13.8 billion years. Its wavelength has been elongated from visible light into the microwave part of the spectrum, making it invisible to our eyes and cooling it to a faint temperature of just 2.7 degrees above absolute zero. This cosmic microwave background, or CMB, was discovered by accident in 1965 by two scientists as a persistent, unexplained hiss in their radio antenna. It is the oldest light we will ever be able to see. It fills the entire sky, coming from every direction, and it is a perfect, ghostly snapshot of the universe in its infancy, a faint, warm echo of the moment of creation. The brilliant, colorful displays we see in images of supernovae are the remains of a truly massive star exploding at the end of its life. Stars that are many times more massive than our Sun live fast and brilliant lives, fusing heavier and heavier elements in their cores. They begin with hydrogen, then helium, then carbon, and all the way up to iron. But iron is a dead end. Fusing it does not release energy, it consumes it. When the star's core becomes iron, its furnace goes out in an instant. With the outward push of fusion gone, gravity wins a sudden and catastrophic victory. The star's core collapses in on itself in less than a second, reaching temperatures of billions of degrees before rebounding in a titanic shockwave. This shockwave, the supernova, blasts the star's outer layers into space at speeds of thousands of miles per second. This explosion is so bright it can outshine its entire host galaxy for a few weeks. But this is not an act of destruction. It is an act of profound creation. It is in the unimaginable heat and pressure of this explosion that all the elements heavier than iron, like the gold in your jewelry, the silver in your coins, or the iodine in your body, are forged. The beautiful, expanding clouds we see, like the Crab Nebula, are the remnants of this process, seeding the galaxy with the heavy elements necessary for building new worlds and, eventually, for life itself. Nebulae are often called stellar nurseries because these vast, beautiful clouds of gas and dust are the active birthplaces of new stars. When we look at deep space photographs, some of the most breathtaking images are of nebulae, vast, ethereal clouds that glow with rich, vibrant colors. These are not just artistic smudges, they are immense interstellar clouds of hydrogen, helium, and cosmic dust. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of the most famous examples. Within these cold, dark clouds, gravity slowly, patiently begins to pull material together. Clumps of gas and dust begin to form, growing denser and denser, spinning as they contract, forming what are called protostars. As these infant stars grow, their cores become incredibly hot and dense, until finally nuclear fusion ignites and a new star is born. The brilliant colors we see in photographs are often the surrounding gas being illuminated by the intense ultraviolet light of these newborn stars, causing the hydrogen to glow a characteristic red. These nebulae are the cradles of the galaxy, the places where the dust of old, long-gone stars is recycled and reformed into new suns and new solar systems, a continuous, gentle cycle of cosmic birth. Astronauts who have returned from spacewalks have reported that space has a distinct and unusual smell. This is a strange concept, as the vacuum of space itself has no smell. There is no air to carry scent molecules to our nose. However, when astronauts return to their airlock after being outside, and they remove their helmets and suits, they consistently report a strong, unique odor clinging to the fabric and equipment. They have described this smell in many ways, often as burnt steak, hot metal, welding fumes, or even burnt almonds or gunpowder. This smell is not the vacuum itself, but is thought to be the scent of space dust, the tiny floating particles that permeate the solar system. These particles are composed of polycyclic aromatic hydrocarbons, PAHs, which are also found in burnt toast, grilled meat, and the exhaust from cars on Earth. These particles, floating in a vacuum and bombarded by radiation, react with the air in the airlock, releasing this distinct, sharp aroma. It is the subtle, metallic, and smoky perfume of the cosmos, the faint odor of the very stuff from which planets and stars are made. The average temperature of the empty space between the stars is incredibly cold, hovering just a few degrees above absolute zero. In the sunlight near Earth, a spacecraft can become scorching hot, but the temperature of space itself is a different concept. Temperature is a measure of the average speed of atoms and particles. In the near-perfect vacuum of deep space, there are very few particles, just a few atoms of hydrogen per cubic meter. These particles are so spread out that they can transfer almost no heat. The only thing warming the vast, empty void is the faint leftover radiation from the Big Bang, the cosmic microwave background. This ancient light bathes the entire universe in a uniform glow that has a temperature of just 2.7 Kelvin, which is about minus 455 degrees Fahrenheit, or minus 270 degrees Celsius. This is just barely above absolute zero, the theoretical point at which all atomic motion stops. This profound, penetrating cold is the baseline temperature of our universe. It is the cold of an ancient, expanding cosmos, a quiet so deep and a cold so vast that it represents the true, undisturbed background state of reality, against which all the warm, bright stars shine like tiny campfires in a vast, dark, and frozen wilderness. The immense gravity of massive objects like galaxies can bend the path of light, acting as a giant gravitational lens. Albert Einstein's theory of general relativity told us that gravity is not a pull, but rather a curve or warp in the fabric of space-time. A massive object, like a star or a galaxy, creates a deep well in this fabric. As a beam of light from a much more distant object travels through the universe, it must follow these curves. If it passes near a massive galaxy cluster, its path will be bent, much like light is bent when it passes through a glass lens. This phenomenon, called gravitational lensing, has been observed many times. It can distort the image of the background galaxy, stretching it into arcs, or even creating multiple images of the same object, as the light takes different paths around the lens to reach us. Sometimes, if the alignment is perfect, it creates a beautiful Einstein ring, a perfect circle of light from the distant galaxy surrounding the foreground object. This cosmic mirage is more than just a beautiful curiosity. It allows astronomers to use these massive galaxies as natural telescopes, amplifying the light from even more distant objects behind them. And it allows us to map the distribution of invisible dark matter by observing the way it, too, bends the light. The brightest and most energetic objects in the known universe are known as quasars. When we look into the deep, distant universe, we are also looking back in time. In the 1960s, astronomers discovered objects that looked like single, faint stars, but their light signatures were bizarre and unlike anything seen before. They were quasi-stellar radio sources, or quasars. We soon realized these were not stars at all, but the active cores of extremely distant, young galaxies. A quasar is, in essence, a supermassive black hole at the center of a galaxy that is in the process of a feeding frenzy. As enormous amounts of gas, dust, and even entire stars fall toward the black hole, they form a superheated accretion disk. This disk of material spins at incredible speeds, and the friction within it heats the matter to millions of degrees, causing it to blaze with a light so brilliant that it can be thousands of times brighter than its entire host galaxy of hundreds of billions of stars. They are beacons in the dark, visible to us across billions of light years. Because they are so distant, they are a window into the toddler phase of the universe, a time when galaxies were young and full of gas, a majestic and fiery epoch in cosmic history, powered by the most powerful engines in the cosmos. The full extent of the observable universe, the part of the universe we can see from Earth, is about 93 billion light-years across. This is a number that strains the imagination, especially when we remember that the universe is only about 13.8 billion years old. How can we see things that are so far away? The answer lies in the constant, ongoing expansion of space. When the light from a very distant galaxy first began its journey toward us, that galaxy was much closer. But in the billions of years that its light has been traveling to reach our telescopes, the universe itself has been expanding. The space between us and that galaxy has stretched, carrying the galaxy much further away. The most distant galaxies we can see today, whose 13.8 billion-year-old light is just arriving, are now, due to this expansion, estimated to be about 46.5 billion light-years away from us in every direction. This creates a bubble of observation, a sphere centered on us, with a total diameter of 93 billion light-years, or about 880 sextillion kilometers. This vast, almost incomprehensible sphere is just the part of the universe we can, in theory, see. The full universe, beyond what our light can ever reach, may be infinitely larger, a concept that leaves us in quiet awe of the scale of our reality. Saturn's largest moon, Titan, is a unique and complex world with a thick, hazy atmosphere and entire lakes and rivers made of liquid methane. When the Huygens probe descended through Titan's atmosphere in 2005, it revealed a landscape that was both alien and hauntingly familiar. Titan is the only moon in our solar system with a dense atmosphere, even thicker than Earth's, composed mostly of nitrogen with a smog of complex organic molecules. This thick, orange haze completely obscures the surface, but beneath these clouds lies a world sculpted by processes we would recognize. The probe and radar mapping from the Cassini orbiter showed us vast plains, dunes made of organic sand, and deep-cut river channels. But on Titan, it is far too cold for liquid water. The surface temperature is a frigid -290 degrees Fahrenheit, or -179 degrees Celsius. Instead, Titan has a methane cycle, just as Earth has a water cycle. It rains liquid methane and ethane from the sky. This liquid flows across the surface, carving rivers, and it pools in vast, still, dark lakes and seas, concentrated at the moon's poles. It is a strange, cold, primordial Earth, a world where the very building blocks of life are being formed in a deep freeze, offering a glimpse of what our own planet might have looked like before life began. Jupiter's moon Europa is one of the most promising places in our solar system to search for life, as it is believed to hide a vast global ocean of liquid water beneath its icy crust. From the outside, Europa appears as a bright white sphere, crisscrossed with long, dark, reddish-brown cracks and streaks. It looks like a frozen, shattered billiard ball, but the data sent back by the Galileo spacecraft revealed a profound secret. This moon's smooth, icy surface, which is remarkably lacking in craters, suggests it is young and geologically active, constantly being resurfaced. The patterns of the cracks suggest the ice shell is not locked to the core, but is instead floating freely. The best explanation for all these clues is that Europa is a water world beneath its crust of ice, which may be several miles or kilometers thick. Lies a deep, salty, liquid water ocean that may be over 60 miles or 100 kilometers deep. This ocean would contain more than twice the amount of water found in all of Earth's oceans combined. This ocean is kept liquid, not by the sun, but by the tidal heating from Jupiter's immense gravity, which constantly flexes and stretches the moon, warming its interior. At the bottom of this dark, alien ocean, it is possible that hydrothermal vents, like those on Earth, are releasing heat and chemicals, creating a potential oasis for life in the deep, cold darkness. The asteroid belt, located between the orbits of Mars and Jupiter, is actually mostly empty space. Our imagination, fueled by science fiction, often pictures the asteroid belt as a dense, chaotic field of tumbling boulders, a place where a spaceship would have to expertly dodge and weave to survive. But the reality of this region is far different and far quieter. While it is true that this region contains millions of asteroids, from small pebbles to the dwarf planet Ceres, the volume of space they occupy is truly incomprehensibly vast. The asteroids are spread out over a region that is hundreds of millions of miles wide. The average distance between any two asteroids is estimated to be over 600,000 miles, or nearly 1,000,000 kilometers, which is more than twice the distance from the Earth to the Moon. In truth, the asteroid belt is a place of profound emptiness. We have sent numerous spacecraft, such as the Voyager, Pioneer, and New Horizons probes, directly through this region without any course corrections, and their chances of accidentally hitting an asteroid were less than 1 in a billion. This vast, invisible belt is not a crowded highway, but a silent, sparse, and lonely wilderness, a scattered remnant of a planet that never was, its pieces drifting in the cold darkness, forever kept apart by the shepherding gravity of Jupiter. Our own sun will one day end its life, not in an explosion, but by slowly puffing off its outer layers to become a beautiful, glowing planetary nebula with a tiny white dwarf at its center. Our sun, the star that gives us life and warmth, is a middle-aged star, calmly fusing hydrogen into helium in its core. It will continue to do so for another 5 billion years. When it runs out of hydrogen, it will begin to fuse helium, and its life will become far more dramatic. It will swell into a red giant, its outer layers expanding so vastly they may consume Mercury, Venus, and possibly even Earth. Its core will become incredibly hot and dense. Eventually, this helium-fusing phase will end, and the core will become unstable. The Sun is not massive enough to explode as a supernova. Instead, it will gently, in a series of thermal pulses, shed its outer layers, puffing them out into space. This expanding, colorful cloud of gas, illuminated by the hot, dying core, is what we call a planetary nebula, named only because they looked like round planets to early astronomers. Left behind at the center will be the Sun's core itself, a white dwarf. This remnant will be an object about the size of Earth, but with the mass of a star, incredibly dense and hot. It will no longer produce new heat, and it will spend the next trillions of years as a glowing stellar ember, a diamond in the darkness, slowly, patiently cooling until it becomes a cold, dark black dwarf. Its long life of giving light and warmth finally at a gentle end. The process of spaghettification is the scientific term for what happens when an object gets too close to the intense tidal forces of a black hole. While black holes do not suck from a distance, their gravity at close range is the most extreme force in the universe. Tidal forces are a difference in gravity. On Earth, the Moon's gravity pulls slightly more on the side of the ocean facing it, creating the tides. Near a black hole, this tidal force becomes unimaginably powerful. If an object, like a person or a star, were to fall feet first toward a black hole, the gravitational pull on its feet would be exponentially stronger than the pull on its head. This immense difference in gravitational force would stretch the object, pulling it apart vertically, while the forces around its circumference would compress it. This process, vividly named spaghettification, would draw any object out into a long, thin, single-file stream of atoms before it even reached the event horizon, the point of no return. It is a powerful, abstract concept, a demonstration of gravity's ultimate power to deconstruct matter itself, not as an act of violence, but as a pure mathematical consequence of the extreme curvature of space-time. It is the universe's most profound and absolute stretching, a final transformation at the edge of reality. A pulsar is a type of rapidly spinning neutron star that flashes like a cosmic lighthouse, sending beams of radiation sweeping across the galaxy. When a massive star collapses, its core, the neutron star, not only becomes incredibly dense, but also retains the star's rotational energy. This causes the new, city-sized object to spin at tremendous speeds, sometimes hundreds of times per second. This rapid spin, combined with the star's original magnetic field, which is now compressed to be trillions of times stronger than Earth's, creates a powerful dynamo. This engine generates intense beams of electromagnetic radiation, which shoot out from the star's magnetic poles as the neutron star spins, These beams sweep through space in a steady, rhythmic pattern. If one of these beams happens to be pointed toward Earth, our radio telescopes will detect a pulse of energy every time the beam sweeps past us. This is not the star itself pulsing, but rather the steady, lighthouse-like sweep of its light. The first one was discovered in 1967 and was so regular that it was momentarily nicknamed LGM-1 for Little Green Men, as its precision seemed artificial. But we now know these are the natural spinning heartbeats of dead stars, celestial clocks ticking away with astonishing precision in the quiet darkness. There is a special class of neutron stars called magnetars, which possess the most powerful magnetic fields in the entire known universe. A neutron star is already an object of extremes, a collapsed stellar core of incredible density, but a small fraction of these objects are born with or develop magnetic fields that are 1,000 times stronger than even a typical neutron star's, and quadrillions of times stronger than Earth's magnetic field. This field is so immensely powerful that it defies comprehension. If a magnetar were located as close as our moon, its magnetic field would instantly wipe the data from every credit card and computer on Earth. If it were even closer, its field is so strong it would distort the very atoms in your body, as the iron in your blood would be pulled from you. The crust of the magnetar is under constant, unimaginable stress from this magnetic field. This stress builds until it suddenly snaps in a starquake, a colossal event that releases a burst of high-energy X-rays and gamma rays into space. These are the most magnetic objects we have ever discovered, stellar ghosts of such profound power that they actively warp their own environment, existing in a constant state of titanic magnetic tension. The most powerful and luminous explosions in the universe since the Big Bang are known as gamma ray bursts. These events are so brilliant that for a few brief seconds, they can release more energy than our sun will in its entire 10 billion year lifespan. For decades, their origin was a profound mystery. They would flash in the sky from random directions, blindingly bright in gamma rays, and then vanish. We now believe they have two different origins. The long bursts, lasting more than 2 seconds, are thought to be the death cry of a very specific massive star, an event called a hypernova, where the star's core collapses directly into a black hole. As this happens, the black hole fires out jets of energy at nearly the speed of light, which blast through the star's outer layers. The short bursts, lasting less than 2 seconds, are believed to be the result of a different cosmic transformation, the majestic merger of two neutron stars, or a neutron star and a black hole, spiraling together in a final cataclysmic embrace. These bursts are flashes of creation, as these mergers are also where a significant portion of the universe's heaviest elements, like gold and platinum, are forged. They are the universe's most intense beacons, visible across billions of light years, marking the violent, beautiful, and creative moments of stellar birth and death. A vast, unseen gravitational anomaly in the distant universe, nicknamed the Great Attractor, is slowly pulling our entire Milky Way galaxy and thousands of other galaxies toward it. For decades, astronomers have been mapping the motion of galaxies in our local corner of the universe. We expected to see them all moving apart, carried by the uniform expansion of space. Instead, we found a flow. Our Milky Way, the Andromeda Galaxy, and the entire cluster of galaxies we live in, the Virgo supercluster, all seem to be streaming in one direction, toward the constellation Centaurus, at a speed of over 1.3 million miles per hour, or about 2.1 million kilometers per hour. This suggests that somewhere over the cosmic horizon, lies an immense concentration of mass, a gravitational basin so deep that its gravity is felt across hundreds of millions of light years. It is slowly pulling us in. The problem is that this region is located directly behind the plane of our own Milky Way, a zone obscured by the thick gas and dust of our own galaxy, making it incredibly difficult to see what lies there. While we have since discovered a massive cluster of galaxies, the Norma cluster, in that direction, it is not massive enough to account for the full pool. The Great Attractor remains a profound mystery, a vast, unseen hand guiding the flow of our local universe, a reminder that we are part of a structure so immense we have not yet even seen its heart. The vast emptiness of space is not uniform. Astronomers have found an enormous, unusually empty region known as the Eridanus supervoid, or the CMB cold spot. When we look at the cosmic microwave background, the ancient afterglow of the Big Bang, we see a map of the infant universe that is remarkably uniform in temperature. However, there is one large patch of the sky in the direction of the constellation Eridanus that is mysteriously, anomalously cold. This CMB cold spot has puzzled scientists for years. One of the leading explanations is that it is not a cold spot in the ancient light itself, but rather the signature of a supervoid, an immense region of space that is almost entirely empty. This void is estimated to be a staggering 1.8 billion light-years across, making it one of the largest structures ever discovered in the universe. It is a place that contains far fewer galaxies, stars, and dark matter than the cosmic average. As light from the CMB travels through this vast emptiness, it loses a tiny bit of energy, making it appear colder to our telescopes. This great, quiet emptiness is a testament to the lumpy, web-like structure of the cosmos, a place where gravity has swept the matter away, leaving behind a profound, cold, and silent expanse, a vast, quiet ocean of near-nothingness in the cosmic web. Astronomers can now study the atmospheres of distant exoplanets by watching them pass in front of their parent stars. When an exoplanet, a world in another solar system, orbits its star, its path may by chance take it directly between us and the star, an event we call a transit. During this transit, the planet blocks a tiny fraction of the star's light, causing a minuscule dimming that our sensitive telescopes can detect. This is how we discover many planets, but this event offers an even more profound opportunity. As the starlight passes through the outer edges of the planet's atmosphere on its way to Earth, the gases in that atmosphere will absorb very specific wavelengths or colors of that light. Different molecules, like water vapor, methane, or sodium, each have a unique fingerprint of light that they absorb. By analyzing the starlight with a technique called spectroscopy, astronomers can see which colors are missing and, from that, determine what the distant world's atmosphere is made of. We have already used this method to find water vapor, heavy metals, and other chemicals in the air of giant gas planets, hundreds of light years away. It is a remarkable, delicate science, allowing us to perform a chemical analysis of the air of another world, a world we will never visit, simply by studying the light that has traveled across the vastness of space to reach us. By studying the vibrations on the surface of our Sun, a science known as helioseismology, scientists can see and hear what is happening deep inside its fiery interior. Our Sun appears to be a calm, steady ball of light, but it is a dynamic, churning, and turbulent place. The immense convection currents, where hot plasma rises and cooler plasma sinks, create sound waves that are constantly ringing through the Sun's interior, like a colossal cosmic bell. These waves are at frequencies far too low for the human ear to hear, with one vibration taking about 5 minutes to complete. These sound waves travel down through the sun's layers and bounce back up to the surface, causing the surface to move up and down in an incredibly complex pattern, rising and falling by several hundred yards or meters every few minutes. By precisely measuring these oscillations with space-based telescopes, scientists can build a detailed map of the sun's hidden interior, just as seismologists on Earth use earthquake waves to map the inside of our planet. This solar sound has allowed us to map the convective zones, measure the sun's internal rotation, and precisely pinpoint the temperatures and densities all the way down to its core. It is a beautiful form of listening, allowing the sun's own deep, resonant voice to tell us the secrets of its hidden heart. The sun occasionally releases massive, powerful bursts of plasma and magnetic fields into space, known as coronal mass ejections. Our sun is not just a source of light and heat. It is an active star with a complex magnetic field. Sometimes the sun's magnetic field lines, which are like giant, invisible rubber bands, become twisted and stressed by the churning, boiling motions of the solar surface. When these field lines suddenly snap and reconfigure themselves, they can release an enormous amount of energy, creating a solar flare, a bright flash of X-rays. Often, this event is accompanied by a coronal mass ejection, or CME, which is a far larger event. This is the physical eruption of a gargantuan bubble of plasma, a cloud of billions of tons of electrified gas, which is violently thrown out from the sun's atmosphere and into the solar system, traveling at speeds of millions of miles per hour. These CMEs travel across space, and if one happens to be aimed at Earth, it can have dramatic effects. While our planet's own magnetic field protects us from the radiation, the impact of this plasma cloud can compress our magnetic field, triggering powerful geomagnetic storms. These storms can disrupt satellites, impact power grids on the ground, and also, as a beautiful side effect, produce the most intense and widespread auroras, painting the high-latitude skies with brilliant, dancing curtains of light. The beautiful dancing lights of the auroras on Earth are the visible result of our planet's magnetic field, protecting us from the solar wind. The sun constantly streams out a flow of charged particles, mostly electrons and protons, which we call the solar wind. This wind travels at high speeds, over 1 million miles per hour, or 1.6 million kilometers per hour, carrying the sun's magnetic field with it. Our planet Earth, however, is not unprotected. It has a powerful, internally generated magnetic field, the magnetosphere, which extends tens of thousands of miles into space. This field acts as an invisible, protective bubble, deflecting the vast majority of the solar wind safely around our planet. However, some of these energetic particles become trapped, and they are funneled down along the magnetic field lines toward the planet's north and south magnetic poles. As these high-energy particles stream down into the upper atmosphere, they collide with atoms of oxygen and nitrogen. These collisions excite the atmospheric atoms, giving them extra energy, which they then release as tiny, beautiful flashes of light. Oxygen atoms glow in shades of green and red, while nitrogen glows in blue and purple. The aurora is, therefore, the beautiful, visible trace of a constant, invisible battle, the light from our atmosphere as it sings under the touch of the sun, a gentle reminder of the invisible shield that quietly keeps our world safe. The dark side of the moon is a misconception. In reality, it is a far side that simply faces away from Earth, and it receives just as much sunlight as the side we see. We are locked in a gravitational embrace with our moon, a state known as tidal locking. This means that over billions of years, Earth's gravity has slowed the moon's rotation so that it now spins on its axis in the exact same amount of time it takes to complete one orbit around the Earth, about 27.3 days. The result of this perfect synchronized dance is that the moon always keeps the same face pointed toward us. This has led to the romantic and mysterious name, the dark side, for the hemisphere we never see. But this name is not accurate. As the moon orbits the Earth, it goes through its phases. When we see a new moon, the side we see is in darkness, but the far side is fully illuminated by the sun. When we see a full moon, the side we see is bright, and the far side is in its own new phase of total darkness. This hidden hemisphere is not a place of perpetual night, but a world that experiences the same cycle of day and night as the side we know, just on a different schedule. It is a land of mountains and craters, first seen by a Soviet probe in 1959, a quiet, hidden face of our nearest companion, bathed in a cycle of sunlight all its own. Despite being the closest planet to the Sun, the surface of Mercury is not uniformly scorching. Astronomers have found definitive evidence of water ice hidden in its polar craters. Mercury is a world of extremes, with a surface that endures a brutal cycle. With almost no atmosphere to trap heat or distribute it, the parts of Mercury facing the Sun can reach temperatures of over 800 degrees Fahrenheit, or about 430 degrees Celsius, hot enough to melt lead. In the long Mercurian night, however, temperatures plummet to minus 290 degrees Fahrenheit, or minus 180 degrees Celsius. It seems like the last place in the solar system to find water ice. And yet, Mercury has a very small axial tilt, meaning it spins almost perfectly upright. This means that at its north and south poles, there are deep craters whose floors are permanently hidden from the sun's rays. These are permanently shadowed regions, places that have not seen a single ray of sunlight in billions of years. In these dark, frigid oases, the temperature is constant and incredibly cold. Data from the Messenger spacecraft confirmed that these shadowed craters contain large deposits of water ice, likely delivered long ago by comet and asteroid impacts. This ice, protected by the permanent dark, has survived for eons, a reservoir of frozen water hidden in the shadows of the solar system's innermost fiery world. We can determine the precise age of our solar system, 4.6 billion years, by studying the chemical composition of ancient meteorites. Our solar system, the Sun, the planets, and all the smaller bodies, is believed to have formed from a single, large, spinning cloud of gas and dust. As this cloud collapsed, most of the material formed the Sun at the center, while the rest formed a protoplanetary disk from which the planets were built. The asteroids and comets are the leftovers of this process, the unused building blocks that were never incorporated into a larger world. When fragments of these asteroids fall to Earth as meteorites, they are like time capsules from the birth of our solar system. Scientists can analyze these meteorites using a technique called radiometric dating. This process measures the decay of certain radioactive isotopes within the meteorite, such as the decay of uranium into lead. By measuring the ratio of the parent isotope to the daughter isotope, scientists can calculate, with great precision, exactly when that rock first solidified from the ancient swirling disk. The oldest of these meteorites, the chondrites, consistently give the same age, about 4.568 billion years old. These humble, ancient rocks that fall from the sky are the birth certificates of our entire solar system. allowing us to touch the very beginning of our own cosmic story. At the very center of our own Milky Way galaxy, there is a supermassive black hole named Sagittarius A star. For a long time, the center of our galaxy, about 26,000 light years away, was a mystery, hidden from our view by thick clouds of interstellar dust and gas, but by using radio, X-ray, and infrared telescopes, which can pierce this veil, astronomers have been able to look into the chaotic and crowded heart of the Milky Way. What they found was a region where stars are orbiting at incredible speeds, some moving at millions of miles per hour. They are whipping around a single central point that is completely invisible, yet clearly has an immense gravitational pull. By tracking the full orbits of these stars over decades, astronomers were able to calculate the mass of this central object with precision. It is a supermassive black hole, a single object with the mass of over 4 million of our suns, all concentrated into a region smaller than the orbit of Mercury. This object, named Sagittarius A star, is not a rampaging monster. It is a relatively quiet and dormant black hole, only occasionally flaring up as it sips on small clouds of gas that stray too close. It is the gravitational anchor of our galaxy, the quiet, massive heart around which our entire spinning island of stars, including our own sun, completes its long 230 million year orbit. Large galaxies, like our Milky Way, are believed to have grown to their immense size by eating or merging with smaller galaxies over billions of years. The universe is not a static place. It is a dynamic environment where gravity is constantly pulling things together. Galaxies are not isolated islands, but a part of a cosmic web of matter. Over the eons, smaller dwarf galaxies are pulled by the gravity of their larger neighbors. As they get too close, the larger galaxy's tidal forces begin to stretch and shred the smaller one, pulling it apart into long, beautiful tidal streams of stars and gas. These streams then slowly orbit the larger galaxy, their stars and gas gradually mixing in with the main population, a process known as galactic cannibalism, or, more gently, galactic merging. Our own Milky Way is currently in the process of absorbing several small dwarf galaxies, including the Sagittarius dwarf galaxy, whose stars are right now being woven into the fabric of our own galactic halo. This is not a violent process, but a slow, majestic, and creative one. It is how galaxies are built, how they gather new gas to form new stars, and how they evolve over cosmic time. This gentle gravitational dance, playing out over billions of years, is the primary way that the grand, spiral structures of the universe are patiently assembled. The empty space between the stars, known as the interstellar medium, is not a perfect vacuum, but is filled with a thin, cold soup of gas, dust, and cosmic rays. When we look up at the dark patches between the stars, it is easy to imagine it as perfect, cold nothingness. But in reality, this space is an environment of its own, the interstellar medium, which is the raw material from which stars and planets are born. This medium is incredibly diffuse. On average, there is only about 1 atom per cubic centimeter, which is a far better vacuum than anything we can create in a laboratory on Earth. This gas is about 99% hydrogen and helium, while the remaining 1% is dust, tiny solid particles of carbon, silicates, and ice, smaller than the particles in smoke. This dust is what blocks visible light and creates the dark, obscuring lanes we see in the Milky Way. This medium is not static. It is roiled by shock waves from supernovae, stirred by stellar winds, and illuminated by the radiation of hot stars. It is the galaxy's atmosphere, its reservoir, and its recycling plant. It is the place where the atoms from old, dead stars wait patiently to be gathered by gravity, to begin the long, slow journey of becoming a new star, and perhaps a new world. Our moon is not locked in a permanent orbit. It is actually, very slowly, drifting away from the Earth. The gravitational dance between the Earth and the moon is a dynamic one, governed by the tides. The moon's gravity pulls on Earth's oceans, creating a tidal bulge of water on the side of the Earth facing the moon and the side opposite it. But the Earth is spinning on its axis much faster than the moon orbits it. This rapid rotation drags that tidal bulge slightly ahead of the moon in its orbit. This leading bulge of ocean water, a massive concentration of mass, has its own gravitational pull, and it tugs the moon forward in its orbit, almost like a gentle tow rope. This constant, gentle tug gives the moon a tiny bit of extra energy, causing it to spiral slowly outwards into a higher orbit. At the same time, this process acts as a brake on the Earth, as the moon's gravity pulls back on that bulge, slowing our planet's rotation. This means that every year, the moon moves about 1.5 inches, or 3.8 centimeters, further away from us, and our day gets longer by about 18 microseconds. This process has been going on for billions of years. In the distant past, the moon was much closer, and Earth's day was only a few hours long. It is a slow, quiet, and profound transformation, the patient, tidal breathing of a planet and its moon, as they slowly, inevitably, drift apart. Astronomers can tell whether a distant star or galaxy is moving toward us or away from us by observing the color of its light, a phenomenon known as redshift and blueshift. This is a cosmic application of the Doppler effect, which we experience on Earth when we hear the pitch of an ambulance siren change as it passes us. As the siren approaches, the sound waves are compressed, raising the pitch. As it moves away, the sound waves are stretched, lowering the pitch. Light behaves in the exact same way. Light from a star is a wave, and if that star is moving away from us, the light waves are stretched out. This stretching shifts the light toward the red end of the electromagnetic spectrum, a phenomenon called redshift. Conversely, if a star or galaxy is moving toward us, its light waves are compressed, shifting them toward the blue and violet end of the spectrum, which we call blueshift. This simple, powerful tool is the foundation of modern cosmology. It was by observing that the light from almost all distant galaxies is redshifted that Edwin Hubble first proved the universe is expanding. It is how we can map the movements of galaxies, watch stars orbit each other in distant systems, and understand the grand, dynamic, and flowing nature of the cosmos, all by patiently reading the language of its light. The term light year is one of the most common units in astronomy, but it is a measure of immense distance, not a measure of time. Because the universe is so incomprehensibly vast, units like miles or kilometers quickly become too small and cumbersome. To measure the space between stars and galaxies, astronomers use the one constant we know, the speed of light. A light year is simply the distance that a beam of light, traveling in a vacuum, can cover in one single Earth year. Given that light travels at about 186,282 miles per second, or 300,000 kilometers per second, this adds up to an enormous distance. One light year is approximately 5.88 trillion miles, or about 9.46 trillion kilometers. Our nearest neighboring star, Proxima Centauri, is about 4.24 light years away, meaning its light takes over 4 years to reach us. Our Milky Way galaxy is about 100,000 light years across, the Andromeda Galaxy, is 2.5 million light-years away. When we say this, it means we are seeing Andromeda as it was 2.5 million years ago, as its light has been traveling through the void for all that time to reach our eyes. This unit beautifully, poetically, and intrinsically links distance with time. To look out into the universe is, by definition, to look back into the past, as we are only capturing the ancient light from these distant, silent objects. The Fermi paradox refers to the profound and unsettling contradiction between the high probability that extraterrestrial life exists and the total lack of any evidence for it. In 1950, the physicist Enrico Fermi was having lunch with colleagues when the conversation turned to the possibility of alien civilizations given the age of the universe, the hundreds of billions of stars in our galaxy alone, and the likely billions of habitable planets. It seems that life should be common. And if just a fraction of that life evolved intelligence and technology, the galaxy should have been colonized many times over by now. Yet when we look up, the sky is silent. There are no obvious radio signals, no giant star-spanning engineering projects, no visitors. This is the paradox. Where is everybody? This simple question has given rise to countless theories. Perhaps life is incredibly rare, and Earth is a unique oasis. Perhaps intelligent life inevitably destroys itself before it can master interstellar travel. Perhaps they are here, but they are observing us, hidden, following a prime directive. Or perhaps the galaxy is full of life, but we are too primitive to detect its signals. The Fermi paradox, or the Great Silence, is a beautiful, humble, and profound question mark. It hangs over our exploration of the cosmos, reminding us of both the vastness of possibility and the quiet, echoing loneliness of our current, known reality. One of the most profound and humbling images ever taken is the pale blue dot, a photograph of Earth captured by the Voyager, one spacecraft from the edge of our solar system. In 1990, as the Voyager 1 probe was completing its grand tour of the outer planets and preparing to coast into interstellar space, the astronomer Carl Sagan made a special request. He asked NASA to turn the probe's cameras around one last time and take a final family portrait of the solar system. From a distance of about 3.7 billion miles, or 6 billion kilometers, Earth was captured as a single, tiny pixel of light. It was a mote of dust suspended in a sunbeam, a tiny, pale blue dot. This single pixel contained everything we have ever known, every human who has ever lived, every king and peasant, every war and every act of creation. The image is a powerful, poetic, and philosophical statement. It is a testament to our profound smallness in the face of the vast, cosmic arena. It shows us that our world is a precious, lonely, and fragile stage in the great, enveloping dark. And it reminds us of our shared responsibility to be kinder to one another and to preserve and cherish the only home we have ever known, this single, quiet, pale blue dot. There is a special type of stellar explosion, known as a Type Ia supernova, that astronomers use as a standard candle to measure the vast distances of the universe. In the grand, dark expanse of the cosmos, it is profoundly difficult to know how far away an object truly is. A star might appear faint because it is small and close, or because it is immensely powerful and incredibly far away. To solve this, astronomers search for standard candles, objects that have a known, reliable, and consistent brightness. The most important of these are Type Ia supernovae. These are not the death of a single, massive star, but rather a binary event. They occur in systems where two stars orbit each other, and one of them is a white dwarf, the small, dense remnant of a sun-like star. This white dwarf patiently pulls material, hydrogen and helium, from its companion star. It accumulates this material, layer by layer, until it reaches a precise critical mass, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. At this exact point, it becomes unstable, and the entire star ignites in a runaway thermonuclear explosion, detonating in a matter of seconds. Because they all explode at the exact same mass, they all reach the same peak brightness, a brilliance as bright as 5 billion suns. By observing how dim one of these explosions appears to us, we can calculate with great precision how far away its host galaxy is. It was by using these reliable, cosmic lighthouses that astronomers first discovered the most profound secret of the universe, that its expansion is accelerating. In 2015, scientists announced the first ever direct detection of gravitational waves, which are invisible ripples in the very fabric of space-time itself. Albert Einstein, over a century ago, imagined space and time not as a static backdrop, but as a flexible, four-dimensional fabric. He predicted that the most massive and violent events in the cosmos, like the collision of two black holes, would not happen silently. They would shake this fabric, sending out waves of gravitational energy that would ripple across the universe at the speed of light. These waves are not light nor sound. They are the physical stretching and squeezing of reality itself. For decades, this was just a beautiful theory. But on September 14th, 2015, two detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, one in Washington State and one in Louisiana, felt an almost imperceptible chirp. This signal was the echo of two massive black holes, each about 30 times the mass of our Sun, spiraling into each other and merging in a distant galaxy over 1 billion light-years away. As these waves passed through Earth, they stretched and compressed the 4-kilometer-long arms of the detectors by a distance 1/10,000th the width of a single proton. This detection was a monumental human achievement. It has opened a brand new sense for us to perceive the universe, allowing us to no longer just see the cosmos, but to listen to its most ancient, powerful, and fundamental rhythms. In 2017, astronomers were startled by the discovery of an object named Oumuamua, the first confirmed interstellar visitor to our solar system. We have always assumed that other star systems, like ours, are filled with asteroids and comets. But the space between the stars is so vast that the chance of an object from another star passing through our neighborhood seemed incredibly small. Then, an object was spotted by a telescope in Hawaii, moving in a way that was unmistakable. It was not in a closed elliptical orbit around our Sun, but on a hyperbolic path, meaning it was moving so fast that it was just passing through, a tourist from afar, destined to swing around our Sun and head back out into the deep. It was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was a strange object, appearing to be long and thin, perhaps like a cigar, and it was tumbling end over end. It also showed no tail or coma of gas like a comet, suggesting it was a rocky, inert asteroid. Strangest of all, as it moved away from the Sun, it seemed to gently accelerate, as if something other than gravity was giving it a tiny push. This faint acceleration is still a mystery. Oumuamua, our first known guest from another stellar family, has now left our solar system, continuing its silent, lonely journey, a fleeting and enigmatic messenger from the great, dark expanse between the stars. In any system with two large orbiting bodies, like the Sun and the Earth, there are 5 special points in space known as Lagrange points, where the gravitational forces are perfectly balanced. We think of gravity as a simple pull toward the center of an object, but in a dynamic, orbiting system, it creates a complex, invisible landscape of hills and valleys. In the 18th century, the mathematician Joseph Louis Lagrange calculated that in the dance between two large bodies, like our Sun and our planet, there are 5 precise locations where a much smaller, third object can maintain its position relative to the other 2. At these points, the gravitational pull of the Sun and the Earth, combined with the centripetal force of the object's orbit, all cancel each other out, creating a gravitational parking spot. 2 of these points, L1 and L2, are stable in one direction but not others, and they lie on the line connecting the Sun and Earth. We have placed many of our most important observatories, like the James Webb Space Telescope, at the L2 point, as it allows the telescope to stay in a fixed, distant position, shielded from the Sun's heat and light by the Earth. The other 2 points, L4 and L5, are truly stable, like gentle valleys in space-time. Here, dust and asteroids have patiently collected for billions of years. Trojan asteroids that travel along with the Earth in its orbit, held in a perfect, quiet, gravitational embrace. Our sister planet, Venus, is a scorching, uninhabitable world today because it experienced a runaway greenhouse effect in its distant past. Venus and Earth are often called twins. They are nearly the same size, have similar mass, and are made of the same rocky material. Venus, being closer to the Sun, was always warmer, but it is believed that billions of years ago, it too may have had vast oceans of liquid water on its surface. But this warmth began a slow, irreversible process. As the oceans warmed, more water evaporated into the atmosphere. Water vapor, like carbon dioxide, is a powerful greenhouse gas, so it trapped more heat, which in turn caused the oceans to evaporate even faster. This created a powerful feedback loop, a runaway process that continued until the oceans had completely boiled away into the sky. The intense ultraviolet light from the Sun then split these water molecules in the upper atmosphere into hydrogen and oxygen. The light hydrogen escaped into space, and the oxygen combined with carbon from volcanoes, forming a thick, crushing atmosphere of carbon dioxide. Today, the atmosphere of Venus is 90 times thicker than Earth's, and the surface temperature is a uniform 900 degrees Fahrenheit, or about 475 degrees Celsius, hot enough to melt lead. It is a quiet, geological cautionary tale, a serene-looking, cloud-shrouded planet that serves as a permanent, silent reminder of how a world's climate can be pushed past a gentle tipping point into a state of profound and permanent transformation. The planet Uranus is unique in our solar system because it is tilted on its side, essentially rolling along its orbit around the Sun. The planets in our solar system all formed from the same spinning disk of gas and dust, and as a result, they all orbit the Sun on roughly the same plane, and they all spin in the same direction, with their axes pointed up relative to that plane Earth, for example, has a gentle 23.5 degree tilt, which gives us our seasons. But Uranus is a profound exception. This ice giant is tilted over by 98 degrees. This means its axis of rotation lies almost perfectly flat with the plane of its orbit. The reason for this extreme tilt is a mystery, but the leading theory is that in the chaotic early days of the solar system, the young Uranus was struck by another large planet-sized body. This immense transformative impact was not a destructive one, but a tilting one, knocking the entire world onto its side. This tilt gives Uranus the most extreme seasons in the solar system. For 21 years at a time, its north pole is pointed directly at the sun, bathing it in continuous cold daylight. Then, for the next 21 years, as it travels to the other side of its 84-year orbit, that pole is plunged into a total frigid darkness. While the south pole takes its turn in the sun, it is a quiet, tilted, pale blue world, forever rolling through the cold, distant darkness. The planet Neptune, the most distant giant in our solar system, is a world of extreme and violent weather, home to the fastest winds ever recorded. Neptune is a dark, cold, blue ice giant, over 30 times further from the sun than Earth. It receives very little sunlight, and its outer atmosphere is one of the coldest places in the solar system, at minus 360 degrees Fahrenheit, or minus 218 degrees Celsius. Because it is so cold and so far from the sun's energy, astronomers expected it to be a quiet, serene, and inactive world. Instead, when the Voyager 2 probe flew by in 1989, it revealed a planet of shocking dynamic beauty. The planet's deep blue atmosphere was streaked with bright, wispy, white clouds of methane ice, and it was home to a great dark spot, a giant swirling storm system similar to Jupiter's. Most stunningly, these clouds were being whipped around the planet by winds of incomprehensible speed. Near the great dark spot, winds were measured at over 1,200 miles per hour, or about 2,000 kilometers per hour. These are supersonic winds, far faster than any hurricane on Earth. This extreme weather is thought to be powered not by the sun, but by Neptune's own internal heat, left over from its formation, which churns its atmosphere from within. It is a world of profound cold. Yet it is alive with a deep, hidden energy, a dark, beautiful, and turbulent king, ruling the silent edge of our solar system. Neptune's largest moon, Triton, is a unique and mysterious world that orbits its planet backwards in a retrograde motion. Nearly every large moon in our solar system orbits its planet in the same direction that the planet itself spins. This prograde motion is the natural result of a moon forming from the same spinning disk of material as its parent planet. Triton, however, is a great exception. It orbits Neptune in the opposite direction, a retrograde orbit, which is a clear gravitational sign that Triton did not form with Neptune. Instead, Triton must have been a wanderer, a dwarf planet that formed in the Kuiper Belt, much like Pluto. Long ago, it must have strayed too close to Neptune and was captured by the giant planet's immense gravity. This capture would have been a chaotic, transformative event, disrupting any native moons Neptune may have had, and settling Triton into its new backward path. Triton itself is a fascinating world, with a cantaloupe terrain of icy plains and a frigid surface of frozen nitrogen. It is also geologically active, with geysers of nitrogen gas that erupt from beneath its crust, cryovolcanoes that spray dark, sooty material onto the bright ice. It is a captured, frozen, and active world, a beautiful prize taken from the Kuiper Belt, forever locked in a slow, backward dance with its captor. Jupiter's moon Io, which is just slightly larger than our own moon, is the most volcanically active body in the entire solar system. When we look at the moons of the solar system, we expect to see cold, dead, cratered worlds. But Io, the innermost of Jupiter's 4 large moons, is a world in constant fiery turmoil. Its surface is not grey and cratered, but a brilliant, mottled patchwork of yellow, red, orange, and black, all painted by sulfur in its various forms. The surface is almost completely free of impact craters, a sign that it is constantly, rapidly being repaved. The Voyager probes discovered that this moon is covered in hundreds of active volcanoes. But these are not all the majestic, mountain-like volcanoes of Earth. Many are calderas, or giant pits, that erupt fountains of sulfur and sulfur dioxide, some spraying plumes of material hundreds of miles high, up to 300 miles, or 500 kilometers, into the vacuum of space, where it freezes and falls back down as a gentle, colored snow. This incredible, constant activity is not powered by internal heat, but by gravity. Io is caught in a relentless tug-of-war between the immense gravity of Jupiter on one side and the smaller, rhythmic pulls of its sibling moons, Europa and Ganymede. On the other, this tidal flexing kneads the moon's interior, generating enormous frictional heat, which melts its rocky mantle and fuels its endless, violent, and beautiful volcanic symphony. Ganymede, the largest moon of Jupiter, holds the distinction of being the largest moon in our entire solar system, and the only moon known to generate its own magnetic field. Ganymede is a world of immense scale, larger than the planet Mercury, and nearly 3/4 the size of Mars. If it were orbiting the Sun on its own, it would easily be classified as a planet. It is a complex, differentiated world with a layered structure, and is believed to have a vast, subsurface ocean of salty liquid water, even larger than Europa's, buried beneath a thick, icy crust. But its most unique feature is something it shares with Earth. Observations from the Galileo spacecraft revealed that Ganymede has its own, internally generated magnetic field, a magnetosphere. This is something no other moon possesses. This magnetic field is thought to be created by a dynamo effect, just like Earth's, caused by the swirling, convective motions within its liquid, metallic, iron-rich core. This mini magnetosphere carves out a small bubble within Jupiter's gigantic magnetic field, creating its own auroras, faint, glowing rings of light. In the thin gas near its poles, it is a moon of superlatives. A giant, complex, and active world. A planet moon that holds the secrets of a liquid water ocean and the unique power of its own hidden magnetic heart. Saturn's small inner moon. Mimas is a quiet, icy world that is dominated by a single, colossal impact crater, giving it a familiar, striking appearance. Mimas is a small moon, only about 246 miles, or 396 kilometers across, and it is made almost entirely of water ice. It is a battered, ancient, and heavily cratered world, a testament to its long history in the busy Saturnian system. But one feature, discovered by the Voyager 1 probe, makes it instantly recognizable. One entire side of the moon is dominated by the Herschel crater, a massive impact basin that is 88 miles, or 139 kilometers wide. This crater is nearly 1/3 of the entire moon's diameter. At its center is a towering peak, rising about 4 miles, or 6 kilometers, high from the crater floor, a mountain almost as tall as Mount Everest. The impact that created this feature must have been an event of almost unimaginable power, a collision that came terrifyingly close to shattering the small, icy moon completely. The shock waves from this impact are visible on the opposite side of Mimas, where the surface is fractured and broken. This small, frozen world, so often noted for its resemblance to the Death Star from science fiction, is a silent, profound monument to cosmic violence, a survivor that wears the scar of its near destruction as its single defining feature. Iapetus, one of Saturn's outer moons, is a world of profound and mysterious contrast, with one entire hemisphere as bright as fresh snow and the other as dark as black soot. This two-faced moon, also known as Saturn's yin and yang, has puzzled astronomers for centuries. Its leading hemisphere, the side that faces forward in its orbit, is incredibly dark, reflecting almost no light. Its trailing hemisphere, the side facing backward, is one of the brightest objects in the solar system. The dividing line between these two regions is not gradual, but surprisingly sharp. The leading theory for this strange paint job is that Iapetus is, in essence, sweeping up dark, reddish-brown dust as it orbits Saturn. This dust is thought to be dusted off of another, more distant, dark, and irregular moon, Phoebe, and is spiraling in towards Saturn. Iapetus, because it orbits in the same direction, flies head-on into this thin cloud of debris. The dark material lands on the leading hemisphere, where it absorbs more sunlight and heats up. This gentle warmth is just enough to cause any ice particles on that side to sublimate or turn directly into vapor, which then refreezes on the cold, bright, trailing side. This process, over millions of years, has made the dark side darker and the bright side brighter, a beautiful, slow, and passive transformation, creating a world of perfect, stark, and quiet duality. Every second, trillions of ghost particles called neutrinos, created in the heart of our Sun, pass directly through your body and the entire Earth as if it were not there at all. In the core of our Sun, the process of nuclear fusion, which powers our world, releases not just light and heat, but also a flood of these tiny, elusive fundamental particles. Neutrinos are one of the most abundant particles in the universe, but they are almost impossible to detect. They have almost no mass, no electric charge, and they interact with other matter only through the weak nuclear force and gravity. This means they are not blocked by matter. To a neutrino, a solid wall of lead several light years thick would be as transparent as a clean pane of glass at this very moment, as the sun shines. More than 100 trillion neutrinos are streaming through every square inch of your body. Every second of every day they pass from the sun's core, through the sun's dense body, across 93 million miles of space, and then pass effortlessly through the entire Earth, from one side to the other, without stopping or slowing down to study them. Scientists have to build enormous detectors, vast tanks of purified water or liquid, buried deep underground to shield them from all other radiation, just to hope to catch the incredibly rare 1 in a trillion collision of a single neutrino with a single atom. They are the universe's silent, invisible messengers, a constant, ghostly rain that connects us directly to the fiery heart of our star. The Earth is surrounded by 2 vast, donut-shaped rings of high-energy trapped particles, known as the Van Allen radiation belts. Our planet's magnetic field, generated by the dynamo of its molten iron core, extends far out into space, creating the magnetosphere. This magnetic field is our planet's invisible shield, protecting us from the constant stream of the solar wind and from dangerous cosmic rays, but this field is also a trap. As high-energy particles, mostly protons and electrons, are blown in from the sun, or arrive from deep space. They are captured by this magnetic field. They do not crash into the atmosphere, but are instead trapped in two distinct, concentric, donut-shaped regions, where they spiral rapidly back and forth between the Earth's magnetic poles at nearly the speed of light. The inner belt, composed mostly of protons, is relatively stable. The outer belt, made of electrons, is much more dynamic, swelling and shrinking dramatically in response to solar storms and coronal mass ejections. These belts, discovered in 1958 by the first American satellite, Explorer 1, are a key part of our planet's space environment. They are a region of invisible, intense radiation that must be carefully navigated by satellites and astronauts, and they are a beautiful, visible demonstration of our world's powerful, protective, and quiet magnetic embrace. Our planet is constantly being bombarded by cosmic rays, which are not rays at all, but high-energy particles, mostly atomic nuclei, that originate from far beyond our solar system. The space between the stars is not truly empty. It is filled with a rain of these incredibly energetic particles. Some are the bare protons of hydrogen atoms, while others are the heavy nuclei of iron, all stripped of their electrons and accelerated to nearly the speed of light. These particles are a form of radiation. Traveling across the galaxy for millions of years, the low-energy ones are thought to be blasted out by normal stars, like our Sun. But the high-energy cosmic rays are a profound mystery. They are thought to be the product of the most violent and energetic events in the universe. The shock waves of exploding supernovae, the jets from supermassive black holes, or the chaotic mergers of neutron stars. When these particles finally end their long journey by striking Earth's upper atmosphere, they collide with atoms of air, creating a shower of secondary, less energetic particles that rain down onto the surface. While our atmosphere and magnetic field protect us from the worst of this radiation, these particles can be seen in cloud chambers, and they are a constant, gentle, energetic hiss from the universe, a faint, subatomic echo of the most powerful, distant, and transformative events in the cosmos. A small, mysterious, and unexplained force was observed to be gently pushing on the Pioneer 10 and 11 spacecraft, the first probes to ever visit the outer solar system. These twin probes, launched in the early 1970s, were our first messengers to Jupiter and Saturn. After their flybys, they continued to coast out of the solar system, their radio signals becoming fainter and fainter. Over the next several decades, as navigators carefully tracked their trajectories, they noticed a tiny, persistent anomaly. Both spacecraft were slowing down, just a tiny bit more than they should have been, based on the known gravity of the Sun and planets. It was as if a minuscule unknown force, equal to just 1/10,000,000th of Earth's gravity, was gently pulling them back toward the Sun. This pioneer anomaly puzzled scientists for decades, giving rise to all sorts of exotic theories, from new laws of gravity to the influence of dark matter. After years of careful analysis of the old data, the mystery was finally solved, not with new physics, but with a much more humble, elegant explanation. The probes were being pushed by their own faint internal heat. The small, plutonium-powered generators that ran their systems produced heat, and this heat was radiating away from the spacecraft, but slightly more in the forward direction. This tiny, asymmetrical push of thermal photons, like the gentlest, faintest rocket thrust, was enough, over decades, to create the mysterious deceleration. It was a beautiful, quiet solution, a testament to the subtle, powerful, and patient forces that govern motion, even in the deep, cold void. The most widely accepted theory for the ultimate, far-distant future of our universe is a scenario known as the heat death, or the big freeze. This is not a sudden, dramatic end, but a slow, gentle, and majestic unwinding. This fate is dictated by the ongoing, accelerating expansion of the universe, driven by dark energy. As space continues to stretch, the galaxies will be pushed further and further apart. In about 100 billion years, all galaxies outside of our own local group will have been pushed over the cosmic horizon. Their light will be stretched so much that they will become completely, irrevocably invisible to us. The sky, outside of our own merged Milky galaxy, will become black and empty. Inside our galaxy, the process of star formation will slowly exhaust the available gas, and one by one, the stars will burn out. Trillions of years will pass. The last, dim, red dwarf stars will finally flicker and die. The universe will be left a cold, dark place of stellar remnants, black holes, neutron stars, and cold black dwarf stars. Even these will slowly decay. The black holes will evaporate over eons through Hawking radiation. The universe will be left as a thin, cold, and quiet soup of photons, neutrinos, and other fundamental particles. Over time, this soup will approach a state of perfect, uniform temperature, just a fraction of a degree above absolute zero. It is the story of a universe that began in a flash of heat and will end as a vast, dark, and perfectly peaceful silence. One of the most profound and sobering hypotheses to explain the Fermi paradox, or the Great Silence, is known as the Great Filter. This idea suggests that in the long, complex journey from simple, non-living matter to an advanced, interstellar, spacefaring civilization, there exists some filter, some step that is so impossibly difficult or dangerous that almost no life in the universe ever makes it past. This filter could be one of many things. It could be that the initial spark of life itself, the jump from simple chemistry to a replicating cell, is so incredibly rare that it has almost never happened. Or the filter could be the jump from simple cells to complex multicellular life, a step that took billions of years on Earth. But there is a more unsettling possibility that the Great Filter lies ahead of us. Perhaps it is a natural part of any intelligent civilization's development that it discovers a technology, like nuclear power or artificial intelligence, that inevitably leads to its own self-destruction. This would explain why the galaxy is silent. No one ever makes it out because they cannot survive their own technological adolescence. This idea reframes the silence of the universe, not as a sign of loneliness, but as a profound, quiet warning. It is a challenge to our own young species to be the one that, through wisdom and care, finds its way past the filter. Astronomers have recently been captivated by mysterious, incredibly powerful signals known as fast radio bursts, or FRBS, which flash from deep space. These are not the gentle, steady pulses of a pulsar. They are single, intense bursts of radio waves that last for only a few thousandths of a second. In that tiny fraction of a moment, they release as much energy as our sun does in an entire day. They are incomprehensibly powerful. We first discovered them in 2007, and for a long time, we did not know if they were a glitch in our telescopes or a real phenomenon. We now know they are real, and they are coming from galaxies billions of light years away. We have found that some of them repeat, flashing irregularly from the same location, which has allowed us to pinpoint their origin. One of the most famous repeaters has been traced back to a magnetar, an extreme type of neutron star with a magnetic field of unimaginable power located in a distant galaxy. This suggests that at least some of these bursts are the result of starquakes on the surface of these hypermagnetic stellar ghosts. But other FRBs, which have never been seen to repeat, may have a different, more cataclysmic origin, perhaps the collision of two neutron stars. They are the newest, brightest, and fastest mystery in the cosmos. Brilliant millisecond-long flashes of light, each one tells us of extreme, powerful events in the silent, distant universe. The theoretical, final stage of a star like our Sun is to become a black dwarf, a cold, dark, and invisible stellar remnant. When a star like our Sun exhausts its fuel, it will shed its outer layers and its core will collapse into a white dwarf, an Earth-sized, super-dense object that glows white-hot, not from fusion, but from its immense leftover heat. This white dwarf will spend eons, trillions of years, in a long, slow cooling process. It has no more fuel to burn, so it will radiate its remaining warmth into the coldness of space, like a dying ember. Its light will slowly dim, fading from white-hot to yellow to orange to red, until it becomes so cold that it no longer emits any significant heat or light at all. At this point, it will become a black dwarf, a cold, dense, invisible ball of degenerate matter, primarily carbon and oxygen, crystallized like a diamond the size of a planet. This is a purely theoretical object. The universe is only 13.8 billion years old, which is not nearly old enough for any white dwarf to have had time to cool down this completely. The process takes so long, perhaps a quadrillion years, that no black dwarfs yet exist. They are not objects of our time, but phantoms of the far, far distant future, the quiet, cold, and final state of rest for the stars that once lit the universe. The Drake equation is not a physical law, but rather a simple, probabilistic argument used to inspire discussion about the number of active, communicating civilizations in our galaxy. In 1961, the astronomer Frank Drake proposed a way to organize our own ignorance. He wanted to estimate the number of civilizations we might one day hear from, so he wrote an equation that multiplies together 7 different factors. These factors start with known quantities, like the rate of star formation in our galaxy, and then move to factors that are educated guesses, like the fraction of those stars that have planets and the number of those planets that are habitable. But the equation's final factors are complete, profound unknowns. The fraction of habitable planets that actually develop life, the fraction of those that develop intelligent life, the fraction of those that develop technology we can detect, and finally, the most uncertain variable of all, the length of time such a civilization releases detectable signals before it fades away. The equation itself cannot be solved, as we do not have the values for most of its terms. Its true purpose is not to give an answer, but to provide a framework. It is a tool for quiet contemplation, a structured way to ask the biggest questions. It breaks down the profound mystery of, are we alone, into a series of smaller, more manageable, and equally profound wonders. The Hercules Corona Borealis Great Wall is widely regarded as one of the largest known structures in the observable universe, a vast, ancient supercluster of galaxies. As we map the universe on the grandest scales, we find that galaxies are not scattered randomly like dust. They are organized by gravity into a vast, beautiful, cosmic web, a filigree of massive filaments, great, flat walls, and dense clustered knots, all surrounding immense, empty voids. For a long time, The largest known part of this web was the Sloan Great Wall, a filament of galaxies over 1 billion light-years long. But in 2013, by mapping the locations of gamma-ray bursts, which are the explosions of massive stars, astronomers detected a concentration of these events in a distant patch of the sky. This clustering suggests an unseen underlying structure of galaxies, a great wall that is so enormous, it strains our very understanding of cosmology. It is estimated to be a staggering 10 billion light-years across. This is so large that light itself would take 10 billion years, almost 3/4 of the age of the universe, to travel from one end to the other. Its existence is a profound puzzle. Our current theories of how the universe evolved suggest that there has not been enough time since the Big Bang for gravity to assemble a single, coherent structure of this almost unimaginable scale. It is a silent, colossal, and quiet challenge to our knowledge, a continent in the cosmic ocean whose shores we are only just beginning to glimpse. The planet Earth is not a perfect sphere. It is technically an oblate spheroid, meaning it is slightly flattened at the poles and bulges at the equator. We grow up seeing globes and maps that represent our world as a perfect, polished marble. But in reality, our planet is a dynamic, spinning object. The Earth rotates on its axis once every 24 hours, and this constant spin creates centrifugal force. This force is strongest at the equator, the part of the planet moving the fastest, and it is zero at the poles. This constant outward push at the planet's midsection, acting against the inward pull of gravity for over 4.5 billion years, has caused our planet to gently bulge. The result is that the diameter of the Earth, when measured from pole to pole, is about 26.5 miles, or 42.7 kilometers, shorter than its diameter when measured across the equator. This also means that if you were to stand at sea level on the equator, you would be further from the center of the Earth than if you were standing at the North or South Pole. This effect is subtle, but it is a fundamental part of our world's shape, a quiet, physical signature of the long, steady, and ancient dance of its own daily rotation. Our moon is covered in a fine, powdery, grey dust known as lunar regolith, which is as fine as flour but as sharp and abrasive as tiny shards of glass. This soil of the moon is not like the soil on Earth, which is created by the erosion of water, wind, and the decay of organic life. Lunar regolith is the pure mechanical product of billions of years of constant micrometeorite bombardment. With no atmosphere to protect it, the moon's surface has been relentlessly blasted by tiny, fast-moving particles from space for eons. This endless sandblasting has pulverized the surface rock into a layer of fine, powdery dust that is, in some places, several yards or meters deep. But because there is no water or wind to smooth the particles, when you look at this dust under a microscope, it is not made of rounded grains, it is made of agglutinates, tiny, jagged, and welded particles of glass and rock, which were melted and fused together. By the heat of the impacts, the Apollo astronauts found this dust to be a profound nuisance. It was stickier than sand, clinging to their suits due to static electricity, and its sharp, abrasive nature wore down their equipment, scratched their visors, and even caused a lunar hay fever when it got inside the lunar module. It is the moon's ancient, sharp, and silent blanket, a record of its long, unprotected history. The Sun is surrounded by a superheated, ethereal outer atmosphere called the corona, which is, paradoxically, millions of degrees hotter than the Sun's visible surface. During a total solar eclipse, when the bright disk of the sun is perfectly blocked by the moon, we are treated to one of nature's most majestic sights, the solar corona. It is a faint, pearly white and ghostly halo of plasma that streams millions of miles out into space. The visible surface of the sun, the photosphere, is an intensely hot 10,000 degrees Fahrenheit, or about 5,500 degrees Celsius. But for a long time, astronomers were baffled by the fact that this outer, thinner atmosphere, the corona, reaches temperatures of 2 million degrees Fahrenheit, or over 1 million degrees Celsius, and in some places even higher. This is the coronal heating problem, a profound mystery of how energy is being pumped from the cooler surface into the thinner atmosphere above it. The leading theories suggest it is a complex process involving the sun's powerful, tangled magnetic fields. These fields, rooted in the sun's interior, are constantly moving, twisting, and snapping in the corona, releasing energy in countless small nanoflares, or sending waves of magnetic energy rippling up from the surface, all of which superheats the thin plasma. This ethereal, invisible except for an eclipse crown is, therefore, a place of profound, magnetic, and quiet turbulence, a furnace hotter than the fire it surrounds. A brown dwarf is a strange and beautiful celestial object that is too large to be considered a planet, but too small to ignite nuclear fusion and become a star. When a star is born, it collapses from a cloud of gas and dust until its core becomes so hot and dense that it ignites the fusion of hydrogen into helium. This process requires a minimum mass, about 80 times the mass of Jupiter. A planet, like Jupiter, forms in a different way, but is far less massive. Between these two categories lies a failed star, the brown dwarf. These objects, sometimes called substellar objects, are born like stars, collapsing from a gas cloud, but they are underweight. They never achieve the pressure and temperature in their cores to start hydrogen fusion. They are, however, massive enough, about 13 times Jupiter's mass, to ignite the fusion of deuterium, or heavy hydrogen, for a short period. After this brief, youthful glow, they simply cool forever and ever. They are not bright like stars, but they are not cold like planets. They glow dimly in the infrared spectrum, radiating their faint, leftover internal heat. They are the universe's in-between objects, the warm, quiet, and lonely embers, forever wandering the galaxy, never quite a star, but always something more than a world. The sun's stellar wind, a constant stream of charged particles, flows outward from the sun and carves a vast, protective bubble in interstellar space known as the heliosphere. Our sun is not just a source of light. It is a dynamic star that is constantly exhaling a stream of plasma, protons and electrons, at speeds of over 1 million miles per hour, or 1.6 million kilometers per hour. This solar wind travels out in all directions, past Mercury, past Earth, past Jupiter, and even past the distant orbit of Pluto. This wind creates a bubble in the thin, cold gas and dust that fills the space between the stars, the interstellar medium. This bubble is the heliosphere, and it is the true boundary of our solar system. The edge of this bubble, where the solar wind is no longer strong enough to push back the interstellar medium, is called the heliopause. This is the region that the Voyager 1 and 2 probes crossed, finally leaving the sun's sphere of influence and entering the cold, quiet darkness of true interstellar space. This vast, invisible bubble, which extends billions of miles or kilometers in every direction, acts as a shield, deflecting many of the dangerous high-energy cosmic rays from deep space, quietly protecting all the planets within its embrace. The dark, shadowy regions on the surface of the Sun, known as sunspots, are actually cooler, calmer regions caused by intense magnetic activity. When we look at the Sun with safe filters, we sometimes see these dark, temporary blemishes on its bright surface. They are not dark because they are black. They are dark only in contrast to the incredibly bright 10,000 degrees Fahrenheit, 5,500 degrees Celsius surface around them. A sunspot is still blindingly hot at about 6,300 degrees Fahrenheit or 3,500 degrees Celsius. These spots are the visible footprint of the Sun's powerful, complex, and local magnetic fields. These fields are so strong in these regions that they poke through the surface, acting like a cork in a boiling pot. They pin down the hot, churning plasma and suppress the process of convection, which is how heat normally rises to the surface. This blocking of the heat transfer is what makes the region cooler, and thus appear darker. These spots are not permanent. They are the anchors of giant magnetic loops that can stretch hundreds of thousands of miles into the Sun's atmosphere. They are the storm centers of the Sun, and it is from these active magnetic regions that solar flares and coronal mass ejections are born. They are the quiet, dark, and cool shadows that betray the presence of the Sun's most powerful and hidden forces. In 2019, an international collaboration of scientists unveiled the first ever direct photograph of a black hole, a supermassive giant at the heart of a distant galaxy. For a century, black holes were just a profound idea, a prediction of Einstein's equations, an object so dense that its gravity traps even light. We knew they existed by the way they pulled on the stars around them, but we could never see one. Its very nature is to be invisible. The Event Horizon Telescope project achieved the impossible by faking a telescope as large as the Earth itself. They did this by linking together 8 powerful radio telescopes from Hawaii to the South Pole and having them all observe the same object at the exact same time. This technique, interferometry, allowed them to combine their data to achieve an angular resolution so high it is the equivalent of seeing an orange on the surface of the Moon. They pointed this Earth-sized telescope at M87, a giant galaxy 55 million light-years away. After years of processing the petabytes of data, they produced an image that was not of the black hole itself, but of its shadow. We see a bright, glowing, asymmetric ring of superheated plasma, the accretion disk, orbiting the black hole at near light speed, and in the center, a perfect, dark, circular shadow, the event horizon, the point of no return, the place where light itself has been captured. It was a momentous human achievement, a moment when we, a small species on a small world, were able to finally and literally look into the eye of the void. The WOW signal, a famous unexplained radio transmission from 1977, was detected at a frequency of 1,420 megahertz, a frequency that is profoundly significant to astronomers. This 72-second long burst of strong, narrow-band radio waves, detected by the Big Ear telescope, remains a profound mystery. But what made it so startling, and what made astronomer Jerry Amon write, "Wow," in the margin, was not just its strength, but its channel. The signal was found at 1,420.4 megahertz. This is the natural emission frequency of neutral hydrogen atoms. The hydrogen line hydrogen is, by far, the most abundant element in the entire universe. Because of this, this specific frequency is like the water cooler of the galaxy. It is a universally known, naturally occurring, and very quiet part of the radio dial, free from much of the background noise of the cosmos. For this reason, scientists have long theorized that if an advanced, intelligent civilization wanted to send a deliberate interstellar hello, a beacon to be found, they would be very likely to choose this exact fundamental frequency. While the signal has never been heard again, and its origin may well be a natural, undiscovered phenomenon, its perfect, accidental alignment with our most profound, hypothetical contact channel is what makes it the most tantalizing and most beautifully poetic mystery in the search for others. Every planet in our solar system that has an atmosphere, including Earth, has an invisible tail, like a comet, that is blown back by the solar wind. We are used to seeing images of comets with their bright, beautiful tails of gas and dust streaming away from the sun. This tail is created as the sun's heat vaporizes the comet's ice, and the solar wind, the sun's constant stream of particles, pushes that material away. Our own planet, Earth, is not a dirty snowball, but it does have an atmosphere. The solar wind exerts a constant pressure on our planet's protective magnetic bubble, the magnetosphere. It squishes the bubble on the side facing the sun and stretches it out on the night side, creating a long, invisible magnetotail that extends for millions of miles, far beyond the orbit of the moon. Within this tail, some particles from the very top of our atmosphere, atoms of hydrogen from our water, are leaking or sputtered away by the solar wind, forming a geotail or geocorona. This is a process that happens on any world with an atmosphere. Venus and Mars, which have weaker or non-existent magnetic fields, are even more susceptible, and their atmospheres are slowly but constantly being stripped or eroded away by this solar wind, their air leaking into space as a long, invisible planetary tail. The planet Mars has two small, lumpy, and irregularly shaped moons named Phobos and Deimos, which are most likely captured asteroids. Unlike our own large spherical moon, the moons of Mars are tiny Phobos. The larger one is only about 17 miles, or 27 kilometers, across at its widest point, while Deimos is even smaller. They are not round, but potato-shaped, and they are dark, heavily cratered, and look exactly like the asteroids we find in the asteroid belt, which orbits just beyond Mars. This has led to the strong theory that these are not native moons that formed with Mars, but rather they are wanderers, two asteroids that, long ago, strayed too close to the red planet and were captured by its gravity, settling into orbits around it. Their orbits are strange and tell a story of a slow tidal dance. Phobos, the inner moon, orbits Mars so fast and so low, faster than Mars itself spins, that it actually rises in the west and sets in the east twice a day. This close orbit is also its doom. Mars's gravity is pulling it closer and closer, and in about 50 million years, it will either be torn apart by Mars's tidal forces, forming a faint, dusty ring, or it will crash into the planet's surface. Deimos, the outer, smaller moon, is in a much more stable, distant orbit and will quietly circle Mars for eons to come. Many of the most essential, heavy elements on Earth, including the gold in our jewelry and the platinum in our electronics, were forged in the cataclysmic collision of two neutron stars. For a long time, we believed that all elements heavier than iron were created in the fiery explosion of a supernova. But our models showed that supernovae, while powerful, could not create the sheer quantity of the heaviest elements, like gold, platinum, and uranium, that we see in the universe. We needed a more powerful, more neutron-rich event. In 2017, we finally saw one. The LIGO and Virgo gravitational wave detectors heard the chirp of two neutron stars, the ultra-dense city-sized cores of dead stars spiraling into each other. Moments later, telescopes all over the world saw the flash of this explosion, an event called a kilonova, in a distant galaxy. By studying the light from this event, astronomers saw the spectral fingerprint of vast quantities of heavy elements being forged and thrown out into space. This single observed event, which lasted only a few days, is thought to have created several Earth masses of pure gold and dozens of Earth masses of platinum. This means that the gold you can hold in your hand, the substance of our wedding rings, was not just born in a star, but was likely created in a fraction of a second, in one of the most violent and rare events in the universe, the majestic, alchemical, and universe-seeding collision of two stellar ghosts. The boiling surface of the Sun is covered in a beautiful cell-like pattern known as granulation, where each cell is a massive churning blob of hot plasma about the size of Texas. When we look at the Sun's surface, the photosphere, with a high-resolution telescope, we see that it is not a smooth, uniform surface. It is covered in a bubbly or rice grain pattern. These granules are the very tops of the Sun's massive convection currents. In the Sun's vast convection zone, which makes up the outer 30% of the star, heat is carried to the surface in the same way it is in a pot of boiling water. Hot, bright blobs of plasma, each one about 600 miles or 1,000 kilometers across, rise up from the interior. They reach the surface, release their heat and light into space, and then, as they cool, they become darker and sink back down in the dark lanes that you see between the granules. This entire process is incredibly dynamic. A single granule only lives for about 8 to 20 minutes before it is recycled, sinking back down and being replaced by a new, hot, rising one. The entire surface of the Sun is a simmering, churning, and seething boil of these Texas-sized convection cells, a beautiful, visible pattern of the colossal, hidden, fiery engine that drives the star's heat. When astronomers talk about metals in a star, they are not talking about gold or iron. They are referring to any and every element on the periodic table that is heavier than helium. In the field of stellar spectroscopy, the universe is seen in very simple terms. The Big Bang, the moment of creation, produced almost nothing but the two lightest elements, hydrogen, about 75%, and helium, about 25%, with a tiny trace amount of lithium. In the language of an astronomer, these are the primordial elements. Every other element, the carbon in your body, the oxygen you breathe, the calcium in your bones, the iron in your blood, and the silicon in the rocks beneath your feet, had to be cooked or forged inside the nuclear furnaces of stars or in their explosive supernova deaths. Therefore, to an astronomer, these elements are all contamination from later generations of stars. When they analyze a star's light, they categorize its composition into three simple groups. X is the percentage of hydrogen, Y is the percentage of helium, and Z is the percentage of everything else. This Z value is what they call the star's metallicity. A very old first-generation star would have a metallicity of nearly 0, while a young third-generation star like our Sun, which formed from the ashes of previous stars, has a relatively high metallicity of about 1.6%. This simple, elegant term is a measure of a star's age and heritage, a quiet chemical record of the generations of stars that had to live and transform before it could be born. And so, our journey through the glittering world of deep space comes to a gentle close. We have drifted far tonight from the familiar light of our own sun, a light that takes 8 minutes to warm us, to the very edges of the observable universe, seeing the ancient, stretched light of the first galaxies. We have stood in awe of the colossal sleeping volcano on Mars, sailed over the liquid methane seas of Titan, and listened to the silent, gravitational song of two black holes merging. We have seen that the cosmos is not just empty, but is a vast, invisible structure of dark matter, a scaffolding for the grand, slow dance of the galaxies. Every story we have told, from the creation of gold in a kilonova, to the gentle, endless rain of neutrinos passing through us, is a part of our own. The universe is not a cold, distant place, but a process, and we are an expression of that process. The iron in our blood, the calcium in our bones, all of it was forged in the hearts of stars that lived and transformed, long before our Earth was even born. You're a way for the cosmos to know itself. And now, it is time for this small part of the universe to rest. If you happen to still be awake, that's perfectly all right. You can simply lie back, let the music keep flowing in the background, and drift in and out of the story at your own pace. But if your eyes are heavy, let the stories of deep space and the gentle music carry you softly into rest. Sleep well. Good night.